Hello there, and welcome back to The Sleep Science. Tonight you're floating in the deep dark where lines don't stay straight and every direction feels a little bit suspect. Above you, stars shimmer like patient old souls, their light curved ever so slightly by the invisible architecture of the cosmos. You probably won't survive this, at least not if you tried to stand on the surface of a neutron star, but don't worry, you're safely horizontal, tucked in with your pillow. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Tell me in the comments where you're listening from and what time it is there. I love seeing the tiny map of humanity light up beneath these cosmic stories. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You float in a darkness that isn't really empty. It's thick with possibility. Particles flicker in and out, and distance itself is something elastic. You reach out a hand and imagine touching space, but there's nothing to touch. It's the stage on which everything else performs, and yet somehow it's also an actor in its own right. You were taught to think of space as a big nothing, a silent void stretching infinitely in all directions, straight lines, flat planes, predictable geometry, the kind you used to draw in school, but space has opinions. It bends around stars and planets, swirls near black holes and ripples when galaxies dance. You just can't feel it because you're too small, and your corner of space-time is calm enough to trick you into thinking it's flat. Still, every step you take on Earth follows a curve. The planet itself is a gentle arc beneath your feet. The idea that space bends sounds poetic, but it's really one of physics' most brutal truths. Imagine standing in a field at night staring up. The light from distant stars travels across billions of years, dodging galaxies and clusters, subtly deflected by the pull of massive objects. That light should travel straight, but straight through what? Straight lines only make sense if space itself is straight, and that's the illusion we're about to peel back. Long ago, people believed the heavens were perfect spheres, stacked crystalline shells turning gracefully around the Earth. That was Aristotle's elegant version of order, and for centuries it felt good enough. Then came a Polish astronomer named Copernicus, gently whispering that maybe it was the sun at the centre instead. He flattened the sky's architecture but didn't question the flatness of space itself. For him, the cosmos was still Euclidean, lines, planes and circles behaving the way your geometry teacher insisted they must. But reality wasn't listening. Gravity kept causing trouble. Objects fell not just toward the Earth, but along invisible pathways defined by its mass. Isaac Newton eventually gave those paths names. He described gravity as a force, an attractive pull between any two masses. It worked beautifully for centuries, predicting everything from apple trajectories to planetary orbits. Yet something faintly absurd lingered in the equations. How could one object instantly know the other's position across the vacuum? Here's where your sleepy imagination gets to flex. Picture the fabric of space not as a grid, but as a stretchable, invisible ocean. When a heavy object like the Earth sits in it, that ocean curves slightly inward. Smaller objects like satellites or the moon follow the slope, gliding along what they think are straight lines but which are in reality the curved geometry of the ocean's surface. You could say they're obeying gravity, or, more elegantly, they're obeying geometry. Historians still argue whether Einstein's greatest insight was intuition or stubbornness. He imagined that gravity wasn't a mysterious tug at all, but a sign that space itself was bending. In his mind, time had to join the dance too, because clocks and rulers would stretch and compress depending on how space twisted. It took years for others to believe him. One proof came during a 1919 solar eclipse, when starlight appeared to bend around the sun, exactly as Einstein predicted. Space wasn't flat, it was doing yoga poses around matter. But you don't need telescopes to feel curvature. Every time you drop something and watch it fall, you're seeing space-time tell matter how to move. Every time you stand up and feel weight, that's space curving you toward Earth's center. You're not being pulled down. Your body is following the shortest path through a curved four-dimensional landscape. Wild, right? And yes, technically, you're falling right now. Your feet are just getting in the way. As you drift in thought, imagine you're inside a huge soap bubble. Its surface curves in 2 dimensions, but from within, it feels endless. That's your life inside curved space. You can't step outside to see the whole thing, but you can watch how light and motion reveal the bends. Astronauts circling Earth experience this too. Their bodies think they're weightless, but they're actually in free fall, tracing Earth's curved geometry again and again. A quirky tidbit for your pillowside trivia bank. Early philosophers once claimed space couldn't possibly bend because nothing cannot be curved. They weren't entirely wrong. It's like trying to fold silence. But Einstein taught us that nothing isn't really nothing. It's an active stage that can stretch, ripple, and bend. Even modern physicists debate what it's made of: fields, quantum fluctuations, or whether it even exists separately from the matter that shapes it. You might wonder, if space can bend, can it also tear? The answer, maybe. Black holes might represent tears, or maybe just extreme folds where all directions point inward. Cosmic inflation might have stretched the early universe so fast it nearly ripped, only to smooth itself into the tranquil cosmic web we see today. The truth is, no one's entirely sure where space stops being geometry and starts being something stranger. So tonight, as you drift towards sleep, think of yourself as part of that bend. Every atom in you is tugging faintly on every atom in the universe, and together, you're helping shape the very fabric of space-time. You're a tiny wrinkle in the grandest blanket ever woven. Not bad for a bedtime thought. You float a little deeper now, letting that idea of curved space settle in like warm tea spreading through your veins. For most of your life, you've trusted your senses to draw straight lines and right angles. Your desk, your phone screen, the hallway lights slanting perfectly from ceiling to floor. It all feels wonderfully Euclidean. But here's the trick. Straight is an illusion that only holds up close to home, like a local gossip that falls apart when you check the facts. You can test this yourself. Next time you're on an airplane, look out the window and watch the flight path on the little digital map. The plane seems to fly in a big arc northward, not straight across the ocean. But that's actually the shortest path on a sphere, a great circle. On the curved surface of Earth, straight lines are bent. You've been living in curvature all along, blissfully unaware. Your brain, though, is stubborn. It insists that walls are vertical, that the road ahead stretches in a neat, endless line. It's not lying, just simplifying. The human visual system evolved for survival on the savannah, not for charting four-dimensional space-time. The flat Earth feeling is an efficient shortcut, like a phone app that compresses data to save bandwidth. Back in the 19th century, long before Einstein came along with his space-time fireworks, mathematicians started to realize that straightness might be optional. Carl Friedrich Gauss, who was allegedly so brilliant he once did mental arithmetic for fun, there's always one, began measuring the curvature of the land in Germany. His results hinted that triangles drawn on large scales didn't quite add up to 180 degrees. Later, Nikolai Lobachevsky and Janos Bolyai formally built non-Euclidean geometry, where parallel lines could diverge or converge. Historians still argue whether they truly grasped that this strange math might describe the actual universe, or merely a thought experiment scribbled between cups of tea. You picture yourself standing on a cosmic grid made of light. When space is flat, those light lines run perfectly parallel. When mass enters the scene, a planet, a star, even your sleepy self, the grid flexes. Light that should travel straight now traces those curves, and so do you. But because you're small compared to Earth's mass, you don't feel the bend. The curvature at human scale is like a hill just a few millimeters tall stretched across a football field. That's why ancient sailors could swear by straight horizons, yet watch Mars disappear bottom first over the sea. The world beneath them quietly curved away while their minds insisted on flatness. It's also why pilots and satellite engineers now rely on geodesics, the curved equivalents of straight lines, to navigate the planet, and why the GPS in your phone corrects for both Earth's curve and a bit of relativity's time-bending tricks. Here's a quirky side note for tonight's trivia. In 1912, before Einstein finished general relativity, he described a thought experiment where you spin inside a rotating disk. The faster it turns, the more the outer edge stretches compared to the center. If you tried to measure the circle's circumference, you'd get a result that violates simple geometry. Space itself, he realized, could behave the same way, stretching and warping in response to motion and mass. The universe, it turned out, was not a polite grid, it was a flexible dance floor. Now, imagine a beam of light leaving a distant galaxy. It travels faithfully straight through the warped geometry of intergalactic space. To you, that path looks bent, but to the photon, it's the straightest possible route, the geodesic of the universe. Light never detours, space itself does the detouring. It's a bit like walking on a curved treadmill that claims you're going straight. The photon doesn't notice, it's too busy racing at cosmic speed limits to care. Some physicists describe this with the term metric, a kind of mathematical ruler that adapts to local conditions. Near massive bodies, the metric changes. The ruler stretches or shrinks so subtly that even clocks slow down. Your heartbeat right now runs microscopically slower than a heartbeat on the top of a mountain, simply because you're deeper in Earth's gravity well. It's not enough to make you late for anything, but the difference is real, and the global positioning system depends on correcting for it. Without those relativity fixes, your GPS would drift by kilometers each day. So yes, your phone quietly negotiates with the bending of space every time you check how late you are for brunch. You may laugh softly at the absurdity of it all. The ground feels steady, time feels constant, yet both are slightly warped. If you could zoom far enough out, you'd see Earth's gravity dimpling space-time like a heavy marble resting on an invisible trampoline. Every straight line you trace, roads, light beams, satellite signals, follows the indentation. And if you push this vision farther, the trampoline itself curves again around the sun, and the sun around the galaxy, until straightness becomes a purely local myth. Historians still debate whether humans are psychologically capable of feeling curvature. Our vestibular systems, tuned for balance, can't sense gravitational warping directly. Astronauts in orbit speak of an uncanny detachment. The Earth looks round beneath them, yet their bodies feel no curve at all. Maybe evolution just decided we'd never need to notice spacetime's yoga poses while chasing antelope. A small, sleepy joke for the road. If you ever feel your life going in circles, remember, it's not you, it's the geometry. The deeper truth is comforting. Curved space means connection. Every object influences the stage, however slightly. Your bed, your breath, your heartbeat. They all add faint ripples to the cosmic weave. And because geometry defines motion, you're constantly in dialogue with the universe just by existing. You move straight through space-time, even when the path looks bent from someone else's perspective. So the next time you see a shooting star streak across the night, realize it's tracing one of these invisible geodesics, a thread of light through the warped fabric. Space isn't bending around you, it's bending with you, shaping a shared map where straight is just a local rumor. You float now through an older dream, a world where space is obedient, clean, and comfortingly flat. The stars are fixed like thumbtacks in a perfect black dome, and gravity is a simple pull, a whisper between masses that never bends or twists the stage beneath them. This is Isaac Newton's universe, and it feels almost quaint after all the cosmic yoga we've just explored. You can almost picture him there in the 17th century, quill scratching in candlelight, the air thick with ink and apple scent. The story goes that an apple fell on his head, though historians still argue whether it ever actually hit him or simply thudded politely nearby. Either way, that moment, real or apocryphal, sparked the grandest realization of its age. The same force that made an apple fall also kept the moon in orbit. Suddenly, heaven and earth were governed by the same law. In Newton's world, space was absolute, a fixed arena where every object had a precise address and time ticked forward like a metronome, impartial and unstoppable. It was an elegant system, so intuitive that it dominated scientific thought for more than 2 centuries. In that perfectly flat cosmos, a straight line was sacred, shortest distance, simplest truth. If 2 points were connected by a line, you could trust that line forever. You drift through that conceptual space now. Everything moves in predictable arcs and ellipses, planets tracing neat ovals around the sun, comets sweeping back on loyal schedules. Gravity is not geometry, it's communication, an invisible messenger telling masses how to pull on each other. Earth tugs on the moon tugs on you. All of it happens instantly across the void. It's satisfying, like clockwork, and you can feel why people clung to it. But even Newton had doubts. His equations said gravity acted instantaneously, faster than light, faster than thought. He once admitted he found that so great an absurdity, he couldn't believe it without divine intervention. Still, no one could offer better math, so the universe remained comfortably mechanical. You glide over the timeline like a dream, seeing ships navigate by stars, artillery arcs plotted with Newton's equations, and orbits calculated down to the hour. In the 1700s, The idea that space itself might be flexible would have sounded like heresy. Space was the stage, not a participant. It didn't bend, it didn't stretch, it didn't care. You might as well accuse your living room of getting emotional when you move the furniture. Here's a historical gem for you. In 1687, when Principia Mathematica was published, it was so dense and revolutionary that most people couldn't understand it, even many scientists. Yet somehow it changed everything. The same equations that described falling apples also guided the future of astronomy, ballistics, and eventually the Industrial Revolution. Newton's flat universe became humanity's mental operating system. Still, there were tiny cracks. Mercury's orbit misbehaved. Its perihelion, that's the fancy term for its closest point to the Sun, drifted slightly more than Newton's theory allowed. It wasn't much, barely a whisper in the math, but it was enough to haunt astronomers. They tried to fix it by inventing a hypothetical new planet, Vulcan, supposedly tugging Mercury off course. Spoiler alert, no such planet existed. The real culprit was space itself, quietly curving around the Sun. But in Newton's day, that idea would have sounded like saying your shadow could have opinions. As you float through this intellectual era, picture how Newton viewed the cosmos, an infinite, immutable container. Time flowed the same for everyone, everywhere. If you dropped a ball in London or on the moon, the ticking of seconds would match perfectly. That consistency felt like a divine guarantee, order built into the bones of reality. For people weary of superstition and chaos, Newton's universe was safe, predictable, comfortingly flat. And yet, there was something lonely about it. The stars didn't talk, they just tugged silently. Gravity had no medium, no carrier, no explanation beyond that's how nature works. The idea of instantaneous action across infinite emptiness, it's like sending a text message with no signal, no network, and still expecting a reply. Newton hated that implication, but his math worked so well that the world shrugged and moved on. Fast forward a century and the cracks widened. Light itself began to misbehave. In 1865, James Clerk Maxwell unified electricity and magnetism and showed that light was an electromagnetic wave, one that travelled at a constant speed, regardless of who was watching. That stubborn constancy broke Newton's flat model of time and motion. Suddenly, the cosmic clock ticked differently for different observers. The stage wasn't as rigid as it seemed. But before Einstein could rewrite the script, the old Newtonian framework ruled supreme. Even today, your car's navigation, your video games, your thrown baseballs, they all obey Newton's math just fine. It's only when you wander near black holes or move at a significant fraction of light speed that the illusion of flat space cracks open. For everyday life, Newton's lie remains a beautiful truth. A little fringe tidbit to tuck under your pillow. Some early Newtonians believed gravity might flow through an invisible medium, an ether that filled all of space. They imagined it as a kind of fluid, denser near massive bodies, explaining why objects fell. It was poetic but doomed. The ether idea lingered for centuries, a ghost theory that refused to leave the party until Einstein politely showed it the door. Still, you have to admire Newton's audacity. With little more than observation and geometry, he described a universe that seemed infinite, ordered, and serene. His flat space was humanity's first map of the cosmos, a projection perhaps, but one that let us reach the moon. You drift now, smiling at the thought that even flatness was once revolutionary. It was the foundation needed for the next leap, the realization that the stage itself was alive, that straight lines were mere approximations of a deeper curvature. For now, you rest in that simpler world. Apple trees, clockwork stars, no ripples, no warps, just the calm ticking of a cosmic metronome. Sleepy, steady, and briefly, perfectly flat. You're still floating in that calm Newtonian expanse when a strange image begins to shimmer behind your eyelids. Someone sitting in a quiet patent office in Bern, 1905, doodling equations on scrap paper while the world outside argues about trains and telegrams. That someone is Albert Einstein, and he's about to commit the most elegant act of mental rebellion in the history of physics. You can almost hear his pencil scratch as he reimagines gravity, not as a pull, but as the shape of the universe itself. He's 26, underpaid, and frequently ignored. You picture him balancing a coffee cup on a pile of letters, eyes half closed, daydreaming about falling. That's where the magic starts. with a fall. Einstein once said his happiest thought was realizing that if you're in free fall, you don't feel gravity. Inside a falling elevator, everything around you floats. Drop a coin, and it hovers beside you. The floor disappears, but so does your weight. For a few beautiful seconds, gravity and motion cancel each other out. You felt a trace of that during turbulence, that fleeting stomach lift as the plane dips. Einstein took that flicker of sensation and built a theory that would upend centuries of thought. Historians still argue whether that insight struck him suddenly, or grew slowly from years of irritation with Newton's instant pull gravity. But once the seed sprouted, the world would never be flat again. He began to suspect that what we call gravity isn't a force at all. It's geometry wearing a disguise. Matter doesn't reach out and pull, it simply tells space how to curve, and curved space tells matter how to move. The universe isn't a stage, it's a participant, bending and stretching as mass and energy rearrange themselves. You imagine him pacing the room, muttering in German, waving invisible objects through the air. The patent office clock ticks indifferently. Outside, trams clang through Bern's cobblestone streets, oblivious that a clerk upstairs is twisting space-time like a towel being wrung dry. In those early years, Einstein was playing with special relativity, his 1905 masterpiece that showed time and space aren't absolute, but relative to the observer. Move fast enough, and clocks slow down, rulers shrink, simultaneity breaks apart like thin glass. But special relativity had one flaw. It only worked when gravity was ignored. And the universe, as you may have noticed, is rather attached to gravity. So he spent nearly a decade wrestling with it, scribbling tensors and symbols that looped like vines. He walked the streets lost in thought, forgetting to eat, occasionally nearly stepping into traffic. His friends worried, but he was deep in conversation with the cosmos itself. Here's a historical tidbit for you. When Einstein finally found the correct field equations for general relativity in 1915, he wept. Literally. They were so beautiful, so inevitable, that he said he felt as though he were merely discovering the structure, not inventing it. The equations said, in essence, matter tells space-time how to curve, and space-time tells matter how to move. It was the ultimate duet. At first, nobody believed him. Even Einstein himself doubted it. His friend and rival David Hilbert published a similar version around the same time, and for a while, the two men danced awkwardly around who had found it first. Historians still argue whether Einstein beat Hilbert by days, or if Hilbert quietly helped shape Einstein's final form. Either way, the new vision stood. Space and time were a single fabric, dynamic and alive. Now picture yourself back in that freefall elevator. The walls shimmer, dissolving into a grid of light that curves gently downward. The objects floating beside you trace invisible lines, geodesics, the straightest paths through curved space-time. When you hit the ground, hopefully metaphorically, it isn't because gravity yanked you, it's because the ground got in the way of your natural straight path. The Earth's mass bends the fabric and you're simply following the geometry. Einstein tested his idea by predicting that light would bend around massive bodies, even though light has no mass. If space curves, photons must follow that curve. In 1919, British astronomer Arthur Eddington led an expedition to photograph starlight during a solar eclipse. When the plates developed, the stars near the sun's edge appeared shifted, just as Einstein predicted. Space had literally leaned under the sun's weight. Overnight, Einstein became a global celebrity, his face suddenly the definition of genius. But fame didn't interest him much. He was too busy thinking about time dilation, the expansion of the universe, and whether God played dice. You smile at that line, it's the one everyone quotes, but what he meant was deeper. He couldn't accept randomness at the heart of reality. He wanted an orderly geometry, even in quantum chaos. A quirky side note, Einstein's colleagues joked that his hair, perpetually wild, mirrored the tangled fabric of space-time itself. When someone asked how he combed it, he replied, "With my fingers, the most efficient tool." Clearly relativity had better uses for his time, yet despite the elegance, not everyone was convinced. Some physicists found the math daunting, others clung to Newton's clean simplicity. After all, general relativity didn't make life easier, it made it weirder. Space could stretch, contract, twist, even trap time in loops, but experiment after experiment confirmed it. Clocks on airplanes ticked slower, GPS satellites had to adjust for time shifts, and starlight curved exactly as predicted. Still, Einstein's daydream had limits. He couldn't reconcile it with the new quantum mechanics rising from laboratories in the 1920s. Relativity described the large, planets, stars, galaxies, while quantum physics ruled the small, atoms, particles, probabilities. The two were like estranged siblings who refused to share a dinner table. Scientists still debate how to unite them a century later. As you drift in your thoughts, picture Einstein gazing out his window at the Swiss Alps, soft clouds curling over peaks. Maybe he smiles faintly, sensing that the mountain's weight bends space-time just enough for light to arc around it. He didn't need a telescope, his mind was enough. And you, lying there half asleep, are quietly doing the same thing. Every moment you exist, you're bending space-time too, ever so slightly, your mass whispering to the cosmos, reshaping geometry in your immediate vicinity. Einstein's dangerous daydream has become the foundation of every motion you make. Gravity isn't a force anymore, it's the poetry of geometry. You drift deeper into Einstein's dream, but the scenery begins to change. Gone are the elegant equations and chalk-dusted blackboards. Now you're in a classroom, and someone has just wheeled out the universe's most famous prop, a big rubber sheet stretched over a metal frame. They drop a heavy bowling ball in the center, and ta-da! You're told this is how gravity works. Space bends, marbles orbit, and suddenly you understand relativity, or so you think. The demonstration is hypnotic. The bowling ball sinks into the stretchy fabric, making a deep circular dimple. You roll a smaller marble around the rim, and it spirals inward, tracing a curved path that feels satisfyingly cosmic. It's a miniature solar system in your hands, but something about it nags at you. The marbles are falling down because of Earth's gravity, not because the sheet itself demands it. The demo cheats. You smile at the thought, gravity explaining gravity with gravity. It's the physics equivalent of using a mirror to check your haircut in another mirror. Still, the image endures. Teachers love it, YouTube loves it. Even some astrophysicists keep it around because it gives the right intuition. Mass warps space, and objects move along those warps. The problem is, it leaves out time, and in Einstein's universe, space without time is like a song without rhythm. You picture yourself standing on that cosmic trampoline, the bowling ball of the sun resting beneath your feet. What you can't see is that the fabric isn't just bending downward, it's bending forward in time. If you could watch space-time as a four-dimensional sheet, you'd see objects tracing elegant spirals through it. Not because they're being pulled, but because they're following straight lines through a curved reality. The planets orbit not around the sun, but through space-time's geometry, always moving straight yet appearing curved to our limited eyes. Historians still argue whether the rubber sheet analogy helped more people understand relativity, or simply cemented the wrong picture forever. Some insist it's harmless, a visual aid, nothing more. Others groan that it tricks students into imagining gravity as a vertical dip instead of an all-directional curve. If the sun truly sat in a rubber sheet, everything would fall straight into it. But that's not what happens. The planets dance sideways, balanced between motion and curvature, like skilled skaters tracing loops on invisible ice. Let's try a different image, gentler and maybe closer to truth. Imagine space-time not as a sheet, but as a dense, invisible syrup filling every corner of existence. Drop a mass into it, a star, a planet, your own sleepy self, and it stirs gentle eddies around it. Motion through this syrup follows the paths of least resistance, the straightest possible routes. You're not sinking or rolling down a hill, you're gliding along a pre-curved flow. That's what geodesics are, straight lines in a bent medium. A quirky fact for your nightstand collection. Einstein himself never used the rubber sheet analogy. He preferred thought experiments with elevators, trains, and beams of light, because he knew the sheet was too easily misunderstood. The visual came decades later, popularized by science communicators trying to make four-dimensional geometry palatable to three-dimensional brains. And really, who can blame them? Imagine a pseudo-Riemannian manifold with non-Euclidean metric tensors doesn't exactly scream bedtime story. Still, the analogy has charm. It helps you see the otherwise invisible, the way mass rearranges space around it, how orbits can be read as curves in a larger structure. Even the imperfections teach you something. Real space doesn't have an external down. It bends internally in every direction at once. You could say the universe is more like a loaf of bread rising from within than a trampoline pressed from above. The curvature isn't on the surface, it's baked in. You glance again at that mental image of the bowling ball sinking into the sheet. Notice the tension, the way the fabric stretches. That's energy being stored in geometry. In the real cosmos, energy and curvature are inseparable. Where matter concentrates, time slows, paths curl and distances stretch. The heavier the object, the deeper the distortion. A black hole would punch straight through the sheet, not because it's heavy in a human sense, but because its mass compresses space and time to a single trembling point. One of the best jokes among physicists, though joke might be generous, is that gravity is what happens when space tells you to take the scenic route. You chuckle softly. It's true. In Einstein's equations, objects aren't being pulled. They're obeying the geometry, faithful to the map even if the road winds unexpectedly. There's something almost spiritual about that, isn't there? The idea that every step, every orbit, every flicker of light is an act of obedience to the shape of existence itself. Even chaos bows to geometry. Yet not everyone was convinced when Einstein first proposed it. Many scientists found the notion of bending space uncomfortably vague. What is space bending into? What's outside it? Einstein's answer was both infuriating and profound. Nothing. Space doesn't bend into anything. It bends within itself. Curvature is intrinsic, not external. Just as an ant crawling on an orange can tell it's curved without ever leaving the peel, we can measure space's curvature without needing an outside perspective. And measure it we have. When light from distant stars bends near the sun, or when galaxies appear smeared into elegant arcs by invisible mass, that's the rubber sheet made real. Only, the universe's version stretches across trillions of kilometers, and the marbles are beams of light that never stop rolling. A small fringe idea once tried to dethrone Einstein's curvature model. Some early 20th century physicists suggested push gravity, where particles streaming from all directions shove matter together. It was clever, but it predicted the wrong heating effects and quietly died out. The rubber sheet, flawed metaphor though it is, outlived them all. So tonight, when you see that iconic demo again in some classroom video, smile at it. Know that beneath its charming simplicity lies a far deeper truth. Space doesn't just sink, it sings. It stretches in rhythm with time, flexes with energy, and ripples when stars collide. You're floating on that fabric right now. You, the bed beneath you, the building, the planet, it's all dimpling space-time together in a cosmic choreography. The sheet doesn't end, it just curves on and on, wrapping everything in gentle geometry. Sleep comes easier when you realize that the universe, even with all its bends and folds, never tears. It only flexes, and somehow, it holds. You float again, this time through something stranger than any rubber sheet. You feel space itself hum beneath you, but now there's another rhythm woven through it, the ticking of seconds. Time has arrived at the party. For the first time, you realize the cosmic fabric isn't just space stretched like taffy, it's space-time, a single, fused entity that refuses to separate into neat categories of here and now. If you could reach out to touch the universe, you wouldn't just feel distance, you'd feel duration. Every step forward is also a step through time, every heartbeat a tiny movement through the fourth dimension. Einstein didn't invent that fusion, Minkowski, his old math professor, did, but he gave it purpose. Hermann Minkowski once declared, "Henceforth space by itself and time by itself are doomed to fade away." Poetic words for a mathematician, and just dramatic enough to make Einstein roll his eyes, at least at first. Later, he admitted Minkowski was right. Without time, space doesn't know how to bend. You drift in that realization, half awake, half measured by cosmic seconds. When mass warps the fabric, it's not just space curling, it's time slowing. The closer you approach something massive, the more sluggish the seconds become. Clocks tick slower near the floor than near the ceiling. A mountain peak lives slightly faster than a valley. You don't notice, but your wristwatch and the satellites overhead are constantly negotiating this difference just to tell you where you are. Without relativity's time adjustments, your GPS would misplace you by kilometers each day. You smile at that thought. Even the calm little blue dot you live on runs a constant conversation between gravity and time. The planet is a patient moderator, reminding both to keep things in sync. You might remember hearing that time is relative, but what it really means is that time is local. Each pocket of the universe experiences its own pace. Imagine standing near a massive star, watching light climb slowly away, its colour stretching red as it loses energy to the star's warped space-time. Far away, an observer sees the light delayed, the clock behind you ticking slower. Both of you are right. There's no single cosmic timekeeper, only the rhythm of each curve. A quick historical flash. In 1976, scientists flew 2 atomic clocks around the world on airplanes and compared them to clocks left on the ground. When the planes landed, their clocks were off, by nanoseconds, exactly as Einstein predicted. It wasn't much, but it was proof that even on Earth's modest scale, space-time stretches and shrinks in real, measurable ways. Here's a quirky tidbit. Astronauts aboard the International Space Station age just a tiny bit slower than people on the ground. They're farther from Earth's gravity, where space-time curves less steeply, so time flows a little faster for them. But because they're also moving quickly, special relativity slows their clocks. The two effects nearly cancel, but not perfectly. A year in orbit adds a few microseconds to their lifespan. Congratulations. Space travel technically makes you younger, though probably not enough to skip sunscreen. Now try to feel this rather than think it. You're lying there, breathing. Each inhale and exhale traces a path through space-time, a smooth ribbon that can never be retraced. The fabric curves gently under the pull of Earth, so your personal timeline isn't perfectly straight. It's subtly bowed. Every object has one, from the candle flickering on a table to the moon itself. The universe, in a sense, is a grand tapestry of timelines woven together, bending, diverging, meeting again. Historians still argue whether Einstein truly understood how radical this merging of time and space was. Some claim he saw it as a simple necessity of math. Others believe he grasped its philosophical weight, that our sense of past, present and future might be illusions stitched by consciousness. In space-time, all moments coexist. The universe doesn't flow, it simply is. You, right now, are as permanent as any star, your entire life mapped out along a curve, from first breath to final sigh, already embedded in the fabric. You just experience it one moment at a time because that's how biological creatures keep their sanity. The idea feels both terrifying and oddly soothing. Nothing is lost, nothing is erased. Every moment still exists somewhere along your world line. The first time you saw the ocean, the last time you laughed until you cried, they're all there, frozen in space-time like shimmering beads on a thread. You may chuckle softly as the thought grows heavy. So technically, you're a 4-dimensional worm, stretching through time. Elegant maybe, but not exactly flattering. The good news? Everyone else is too. Now consider what happens when a massive body enters this picture. A planet, a star, a black hole. It doesn't just warp the spatial coordinates, it bends the timeline itself. Near a black hole, time slows so dramatically that to a distant observer, an object falling toward it seems to freeze at the edge forever. But from the falling object's perspective, it continues smoothly inward, past where time itself has curled so tightly it can't unfold again. That's the power of merging time and space. Events become geometry. You can draw them, predict them, and sometimes even escape them, though not from black holes, of course. There's another debate that hums softly among physicists even now. Is space-time a fabric we live in, or a network we live as? Some theories suggest space-time itself might be emergent, a collective illusion rising from deeper quantum relationships, like waves forming on an unseen ocean. If that's true, then even the bending we're talking about tonight might just be a large-scale side effect of something far smaller and stranger. But don't worry, we'll wander there later. For now, just stay in this moment, a single smooth dip in the flow of space-time. Imagine you're floating near Earth, watching the curve of the horizon beneath you. The planet's mass bends the grid softly, and your clock ticks a fraction slower than one far from the sun. Everything feels gentle, rhythmic, inevitable. Space and time have stopped pretending to be separate. They've intertwined, hand in hand, keeping the cosmos in motion, guiding every planet's path, every heartbeat, every whisper of light. The universe doesn't just bend around matter, it sways with it, a timeless waltz that never stops. And whether you're awake or already half asleep, you're part of that waltz right now. You float in that waltz a little longer, watching how space-time folds and dips around heavy objects like velvet under the weight of jewels. You've seen the metaphor, Earth's gentle dimple, the sun's deeper bowl, but now you're ready to step closer, peer over the edge, and see what those bends actually do. Because when you stare long enough, the geometry of gravity begins to reveal its secret shapes: wells, slopes, and swirling funnels carved into the invisible. Imagine for a moment that you're hovering above the sun. You can't feel the heat. This is a dream after all, but you sense the curvature below you, a grand depression in the space-time fabric. Planets drift along its contour lines, not pulled, but guided. Mercury skims the deepest curve, hurtling around the sun so fast it almost feels the drag of time itself. Farther out, Jupiter strolls along a shallower path, its enormous bulk adding its own little dent to the overall architecture. From up here, gravity wells look like a landscape, mountains and valleys made of geometry. Matter piles up, and space sinks in. Every planet, moon and star carves its own basin in the cosmic terrain. You can almost see it, a three-dimensional topographic map of space-time, where every dip corresponds to mass, and every slope determines motion. You might think things should roll straight to the center and vanish, but that's not how it works. The secret lies in motion itself. Earth, for instance, is constantly falling toward the sun, but because it's moving sideways fast enough, it keeps missing. Like a marble rolling around a funnel, it circles endlessly, tracing a stable orbit through curved space. You, at this very moment, are falling too, perpetually falling toward the sun, toward the galactic core, toward every gravitational well in sight, but never quite hitting bottom. It's a comforting thought, really. The universe has turned free, fall into choreography. Here's your historical anchor for the night. Johannes Kepler, in the early 1600s, described the precise elliptical paths of planets long before anyone understood why they moved that way. His 3 laws of motion were mathematical poetry, but he couldn't explain the reason behind them. Centuries later, Newton supplied the why with his laws of gravity. Then Einstein came along and replaced both with something stranger. There is no why. The planets simply follow the straightest paths available, and a curved space-time historians still argue whether Einstein's answer solved the mystery or just gave it new vocabulary. A quirky tidbit. In 2013, a physicist at MIT built a gravity well using nothing more than stretched spandex and metal balls, trying to visualize planetary orbits for students. It worked beautifully, until one of the smaller balls decided to rebel, slingshotting out of orbit and landing squarely in a cup of coffee. Even the universe, it seems, has a sense of humor about its metaphors. Back to your floating perspective. As you gaze at the sun's well, you notice the slope isn't infinite. There's no cliff edge, no hole punched through the fabric, just an increasingly steep descent. Space and time twist together more tightly the closer you approach, until time itself begins to lag. Clocks slow, light bends, and motion turns inward. That's what curvature is. Not just a warping of direction, but a warping of possibility. You can trace this same pattern across the cosmos. Around Earth, space-time forms a modest dip. Around Jupiter, the dip deepens. Around the Sun, it plunges further still. But near a neutron star or black hole, geometry goes wild. There, the slope becomes so steep that no motion, not even light, can climb back out. That's not just a gravitational pull, it's geometry closing in on itself. You picture the concept as a kind of gravitational topography, each star and planet nested inside another's bowl, all of them stacked in the galaxy's grand depression. If you could flatten that map, it would look like a cosmic fingerprint, ridges and grooves encoding the history of everything that's ever existed. Every collision, every orbit, every galaxy cluster leaves a subtle mark, reshaping the local curvature. You too contribute your own minuscule indentation. It's faint, but real. You wonder briefly what it means to fall in a world where everything's already curving. Gravity wells are less about attraction and more about geometry's efficiency. The universe prefers elegance. It lets motion happen along the simplest paths. You, in orbit or in bed, are always gliding along one of those paths, guided not by force but by form. Historians still debate whether Einstein himself fully grasped the visual implications of his theory. He rarely described gravity wells, preferring pure math to imagery. The funnel-like shape we picture today came later, courtesy of artists trying to give form to four-dimensional equations. But maybe that's what makes it so mesmerizing. Humans can't help translating math into landscapes. A fun thought before you drift further: gravity wells are also wells of time. The deeper you are, the slower your clock ticks relative to those higher up. So when astronauts climb from Earth's surface into orbit, they're literally ascending out of slower time. If you could hover near a massive star, time around you would crawl compared to distant space. In a sense, every gravitational well is also a temporal swamp, where seconds stretch like syrup. You might even whisper to yourself, "I live in a gentle well," because you do. Earth's curve holds you softly, slows your days by the tiniest margin, and lets you orbit the sun like a leaf drifting on an invisible current. A little joke, for the sake of the sleepy mood. Technically, you're falling forever but doing it perfectly. NASA could put that on a t-shirt. Professional fallers since 1961. So as you float above the invisible contours of space, take comfort in the thought that nothing in the universe moves in straight lines. Everything swirls, drifts, precesses, and curves. Even the galaxies themselves orbit deeper structures of gravity like nested spirals in an endless seashell. Space bends because it must. Time follows because it can. And you're the lucky passenger, tracing graceful arcs across the universe's invisible hillsides. You drift over one of those invisible hillsides now, still suspended in the soft darkness of space-time. Beneath you, the geometry tightens. Gravity is no longer just a silent slope, but a hand on the shoulder, guiding even light itself. That's the real giveaway that space is bent, when the fastest, straightest traveller in existence, a beam of light, can't resist the curve. Imagine this. You're standing under a sky so perfectly black that stars look like holes in reality. Somewhere out there, a beam of light leaves a distant galaxy. It doesn't wander or weave, it shoots off in what it believes is a straight line. But the universe has other plans. Between you and that faraway galaxy lies the sun, a modest but powerful distortion of space-time. When the light passes close, it bends slightly inward, curving around the sun's mass before continuing on its way. By the time it reaches Earth, it appears to come from a slightly shifted position in the sky. The star's light has been deflected, and you, tiny observer on a spinning rock, have just caught space in the act of bending. That's not fantasy, it's history. In 1919, a total solar eclipse gave scientists the perfect chance to test Einstein's bold prediction. Astronomer Arthur Eddington packed up telescopes, film plates, and optimism, sailing to the island of Principe off the coast of Africa. During the few minutes of total darkness, he photographed stars near the eclipsed sun. Later, when he compared those positions to where the same stars appeared at night, the difference was there, tiny but unmistakable. Light really had curved. Einstein's theory wasn't just clever, it was true. Newspapers around the world shouted the headline, "Revolution in Science, Newtonian Ideas Overthrown." Historians still argue whether the data were strong enough to justify that excitement. Some say Eddington's results were fuzzier than he admitted. But even if the evidence was modest, it lit the fuse of relativity's fame. Overnight, Einstein became the face of modern genius, and the bending of starlight became a bedtime story for the whole planet. You might smirk a little, thinking about how poetic it is that light, the universal speed limit, isn't immune to gravity. It doesn't slow down, it just changes direction, following the warped contours of space itself. To light, the detour is the straight path. It's not breaking rules, it's obeying geometry's new ones. Here's a quirky tidbit to keep the mood gentle. Decades after Eddington, physicists began using this same principle, light bending, to create natural telescopes. They call it gravitational lensing. When a massive galaxy cluster sits between us and something even farther away, the cluster's gravity warps space-time enough to bend and magnify the background light. The result? We see distorted rings, arcs, and doubled images of distant galaxies. Astronomers nicknamed one of these patterns Einstein's cross, another the cosmic horseshoe, and yet another the Cheshire cat. The universe apparently enjoys cosmic wordplay. If you could drift near one of those gravitational lenses, it would look surreal. The stars wouldn't twinkle, they'd smear, multiply, form shimmering halos. every photon would be whispering, "I took the long way around." And you'd realise, perhaps with a sleepy smile, that straight is just perspective. Light bending also means gravity can act like a mirror, a magnifying glass, and even a time machine. Some lenses delay the arrival of light from different paths, so we see the same cosmic event, like a supernova, flashing multiple times years apart. The universe keeps replaying its highlights for anyone patient enough to watch. Now picture this on a smaller scale. Light passing near Earth bends too, but the angle is microscopic. It's enough, however, for modern instruments like the Hubble and James Webb telescopes to notice. When they map distant galaxies, they have to account for every distortion caused by passing through the galaxy clusters in between. It's like looking through a window pane that's subtly rippled. And yet, thanks to those ripples, we can see objects far beyond what our own telescopes could reach unaided. You lie there, half dreaming, and imagine the light that just reached your eyes. Maybe it came from a star in Orion, 100 trillion kilometers away, dodging asteroids, brushing past planets, bent by the Milky Way's invisible halo of dark matter. Each photon took its own unique route, curved by countless tiny gravity wells, before ending its centuries-long journey on your retina. You blink, and the light's story ends. Historians still debate how much Eddington's expedition mattered to Einstein himself. Some say he basked in the fame, others insist he barely cared. What is certain is that after that eclipse, relativity stopped being theory and became reality. Space bent, time flexed, and the universe lost its straight edges forever. And if you're wondering what happens when light bends too much, when curvature becomes so extreme that photons can't escape at all, well, that's where black holes come in. But we'll get there soon. For now, savour this gentler picture. Space is a lens, not a trap. It plays with light like glass, plays with sunlight, bending, stretching, making art out of distortion. A small sleepy joke before you drift further. Somewhere, a photon is late to its destination because it took the scenic route around a galaxy cluster. Light, it turns out, has zero patience for straight lines. So next time you gaze up at a star, remember, the position you see isn't where the star truly is. You're looking at a bent truth, a piece of light that swerved through cosmic geometry just to reach you. Even in its deflection, it's faithful. And as your eyes grow heavier, that light fades softly into memory. Curved, delayed, but beautifully persistent. You linger on that image of the starlight bowing around the sun, and the thought pulls you deeper. Because if the sun's gravity can bend light a little, what happens when the curve grows so steep that light can't climb out at all? That, sleepy traveller, is where the geometry goes feral. Welcome to the place where space-time folds in on itself, the black hole. You can feel it before you see it, a silent distortion that steals sound and starlight alike. There's no wall, no smoke, no glowing edge, just a region of space so deeply curved that every possible path, every geodesic points inward. It isn't a hole in space, it's space itself gone vertical. It started, like most cosmic horrors, as math. In 1916, just a year after Einstein published General Relativity, a German physicist named Karl Schwarzschild wrote to him from the front lines of World War I. Between artillery calculations and chaos, he had found the first exact solution to Einstein's equations, a description of what space-time would look like around a perfectly spherical mass. Historians still marvel that he did it in a trench, surrounded by mud and explosions, as if the universe had decided that wartime was the perfect backdrop for pure thought. Schwarzschild's solution included something odd, a point where the curvature became infinite. He didn't think much of it, it was just math misbehaving. But decades later, physicists realized that point represented something physically real, a place where gravity became so strong that even light couldn't escape, the black hole. Here's the fringe tidbit. The name itself didn't appear until the 1960s. Before that, they were called frozen stars, or dark bodies. When physicist John Wheeler finally coined black hole, some journalists found it scandalous, too suggestive, too impolite for newspapers. But the term stuck, probably because it was perfect. You float closer. From your distant vantage, it looks deceptively calm. Stars orbit it gracefully, drawn to its mass but not doomed. There's no danger until you cross the event horizon, that invisible boundary where escape becomes mathematically impossible. Outside it, light can still turn and flee. Inside, every future leads inward. If you could hover just above that horizon, time for you would slow almost to a stop. A clock on your wrist would tick lazily while the rest of the universe raced ahead. From your perspective, everything seems normal, you drift inward. But to a distant observer, you freeze at the edge, light from your body stretched and reddened until it fades into black. Historians still argue whether that frozen image means you never truly cross from their perspective, or whether it's just the universe's cruel way of saying goodbye. Now imagine you ignore all that and keep falling. You wouldn't notice the exact moment you cross the horizon. There's no bump, no spark, no warning. But soon the curvature grows unbearable. The laws of physics, steady companions until now, start to contradict themselves. At the very centre waits the singularity, a point where space-time's curvature becomes infinite, where every equation collapses. General relativity breaks there, like a violin string pulled too tight. What does that mean? Nobody truly knows. Maybe the singularity doesn't exist in the literal sense. Maybe quantum physics, that mischievous rival, softens the blow. Some theories suggest black holes hide Planck stars, ultra-dense cores where space stops collapsing because quantum effects push back. Others whisper about wormholes, passages to other universes folded within the equations. Historians still debate whether Einstein himself believed in such exotic possibilities. He called singularities unphysical, yet his equations refuse to behave otherwise. You drift around the black hole now, tracing its geometry with your mind. The event horizon isn't a surface, but a sphere of inevitability. Space and time swap roles there. Space becomes something you must move through like time, and time becomes a direction leading only inward. There's no pause button, no return. Even light's best attempt to hover fails. Photons orbit once, twice, then spiral in. It sounds terrifying, but the edges of black holes can be strangely beautiful. The space just outside glows with radiation from falling matter, disks of plasma whirling at near-light speeds, magnetic fields twisting into cosmic storms. From a safe distance, you could see the light bending full circle around it, forming a glowing ring, the photon sphere, its light's last stable orbit, a shimmering halo of self-gravitating brilliance. When the Event Horizon Telescope released its first image of a black hole in 2019, that's what we saw. Not the hole itself, but that ring of tortured light. The data came from telescopes scattered across Earth, combined into one planet-sized eye. The result looked eerily familiar, exactly like Einstein's equations predicted down to the last luminous curve. A little sleepy joke here. Somewhere out there, a photon tried to photobomb the picture but got caught in orbit instead. Eternal blooper reel. But there's something oddly comforting about black holes. They're not cosmic monsters. They're the universe's recycling bins. Every galaxy seems to host one at its core, quietly orchestrating star formation, shaping galactic structure. Without them, spiral arms wouldn't hold together, and the Milky Way might never have been born. They're destructive, yes, but also deeply necessary, like forest fires that make room for new growth. If you could survive the fall, and you can in dreams, you'd discover that time doesn't end at the horizon. From your point of view, you'd continue falling normally, passing layers of reality where space folds tighter and tighter until direction itself dissolves. At some point there's no longer an up or down, only in. And yet the strangest part, information, the details of everything that falls in, might not vanish. Quantum physics protests. Hawking radiation, predicted in 1974, suggests black holes slowly leak energy, perhaps carrying that information back into the universe. Stephen Hawking himself spent decades wrestling with the paradox, changing his mind more than once. The debate still hums quietly among physicists like static at the edge of time. You meanwhile float safely outside the danger zone, letting the enormity of it all wash over you. Space can bend so far that it folds. Light can be trapped by its own straight path. Time can freeze, stretch, collapse, or vanish. And yet, somehow the equations still make sense until they don't. So as your thoughts drift and your breathing slows, picture yourself as a faint ripple orbiting that darkness. You're tracing geometry's most dramatic performance, where gravity stops pretending to be gentle. And in the quiet hum of space-time, even a black hole feels like part of the same universal lullaby, just a deeper note in an endless song. You linger near the shadow of that black hole, the hum of its curved geometry still thrumming in your ears when something catches your eye. A faint shimmer, a distant arc of light that seems to loop impossibly around a cluster of galaxies. You blink once, and suddenly you're looking at a cosmic mirage. The light isn't where it should be, and yet it's utterly real. Welcome to the universe's art gallery, the realm of cosmic lenses and mirrors. You drift closer, and the shapes sharpen. A halo of light surrounds a dim heart, stretched into a perfect ring, Einstein's ring. It isn't magic, it's geometry once again, playing tricks on perception. A massive galaxy or cluster sits in the foreground, its gravity bending light from something even farther away. That distant galaxy's light takes multiple curved routes through warped space-time, reaching you as overlapping, magnified images. You're not seeing one object, you're seeing several versions of it stitched together by curvature. It's the same principle that guided Eddington's eclipse photos, but now scaled up to galactic grandeur. The bending isn't measured in arc-seconds anymore, it spans whole constellations. You might call it gravitational lensing, but the universe might call it showing off. Historians still debate whether Einstein himself predicted this phenomenon deliberately or almost by accident. In 1936, a friend named Rudi Mandl asked him to calculate how light from one star might be bent by another. Einstein did the math and concluded that, while theoretically possible, the alignment needed was so precise that there is no hope of observing this phenomenon directly. He filed the paper away almost as a curiosity. A few decades later, telescopes began finding them everywhere. Even geniuses can underestimate the universe's flair for irony. Now you're floating in front of one of these lenses, a cluster of galaxies so massive it could host thousands of Milky Ways. Their combined gravity sculpts the space around them, turning it into an enormous optical device. Light from galaxies billions of light years beyond streams through, splitting into arcs, curves, and ghostly reflections. You can see entire galaxies duplicated, mirrored, magnified, some warped into elegant rings, others stretched into long streaks like taffy. It's strangely beautiful. The universe doesn't just bend space, it paints with it. You notice something else. This lensing doesn't only create pretty pictures, it's also a tool. Astronomers use these distortions to measure mass, including the invisible kind. The amount of bending reveals how much gravity hides inside the cluster, and when they add up the numbers, they find a mystery. There's far more curvature than visible matter can explain. The culprit is the elusive dark matter, a topic we'll wander into soon, but for now, know this. These cosmic lenses are how we see what we can't see. A quirky bedtime fact. One of the most famous gravitational lenses, nicknamed the cosmic horseshoe, was discovered in 2007 not by professionals, but by a university student scanning Sloan Digital Sky Survey images. The arc looked exactly like a horseshoe of light wrapped around a blue galaxy. Scientists later confirmed it was a perfect example of Einstein's ring, nearly textbook in its precision. Somewhere out there, a starry horseshoe is bending light and probably still bringing a little luck to the astronomers who found it. You glide farther, watching these rings overlap into delicate patterns. Some lenses create quadruple images, 4 points of the same quasar arranged like a cross. Others produce near-perfect circles, where the background galaxy aligns precisely behind the foreground one. Every pattern is unique, like fingerprints of curvature, and there's time hidden in these shapes too. Each pathway the light takes is a different route through space-time, and those routes have slightly different lengths. That means you're not just seeing multiple images, you're seeing different moments of the same object. A supernova might explode in one arc, then days or even years later in another, as the delayed light finally arrives. The universe becomes its own time-lapse photographer, endlessly replaying the same explosion from slightly different angles. Historians still argue whether lensing was the first definitive evidence for dark matter or just the prettiest clue. Either way, it transformed cosmology. Suddenly, we could measure gravity directly by how much it bends light, not just by how stars move. Space had become a lensing laboratory, and every galaxy cluster a cosmic mirror maze. You chuckle softly. If Newton could see this, he'd probably insist on polishing the mirrors. You can test the same principle closer to home, in miniature. When you look at the distorted edge of a glass of water, or watch heat shimmer over asphalt, you're seeing light bent by tiny gradients in density. Gravitational lensing is the same idea on an unthinkable scale. The glass is space-time, its curvature changing with mass. Instead of rippled air or curved glass, it's whole galaxies doing the refracting. Here's a sleepy joke to ease the math away. When the cosmos gives you lemons, it probably just bent them into a lemon-shaped ring around a galaxy cluster. If you could float long enough among these cosmic optics, you'd see that the entire sky is full of them, most too faint for your eyes, but all there. Every photon you receive has taken a winding path through a field of invisible curves. The night sky you love isn't just a map of stars, it's a palimpsest of bent light, each point of twinkle already shaped by gravity before it touched you. The James Webb Space Telescope, with its golden mirrors, now peers through these natural magnifiers to see deeper than ever. Some of the galaxies it photographs are visible only because space-time itself has lent a helping hand, magnifying them dozens of times. It's the universe holding up a mirror so we can admire its own reflection. And so you drift among these luminous arcs, their light delayed by billions of years, their forms twisted into poetry by geometry. Space doesn't just bend, it reveals. It turns gravity into vision, curvature into art. You exhale softly. Somewhere behind all this bending, behind all the mirrors and lenses, the original sources still shine. Their light just took the scenic route, looping through the cosmic fabric to reach your sleepy eyes. The next time you look up, know that you're gazing through a hall of mirrors so vast that even infinity has to squint. The universe feels hushed again, but the silence carries a tremor now, a rhythm so faint you can't hear it, only sense it through the bones of space itself. The fabric that once seemed smooth and still is quivering, like the surface of a pond after a pebble's fall. You're floating among ripples in space-time, the ghostly echoes of cosmic events that happened long before you were born. At first, Einstein himself didn't believe they were real. When he first predicted gravitational waves in 1916, they were merely a side effect of his equations, elegant but suspiciously elusive. He even changed his mind a few times, first certain they existed, then doubting they could ever be detected, then finally shrugging as if to say, well, maybe the universe hums after all. Historians still argue which version of Einstein they prefer, the confident prophet or the reluctant realist. You can picture it easily now. Two massive bodies, say, a pair of black holes, spiral around each other, faster and faster, until they merge. The energy released doesn't travel as light or heat, but as waves in space-time itself. These ripples stretch and squeeze the very distance between things, expanding and contracting reality by less than the width of a proton. That's all, but it's enough to shake an entire planet ever so slightly. A sleepy smile creeps across your face as you realize you're riding those waves right now. They pass through you constantly, faint vibrations from ancient collisions across the universe. They ripple through the earth, through your pillow, through the air between your breaths, changing everything by microscopic amounts, and yet you never notice. To detect something so subtle took a century of patience. The story begins with a project called LIGO, the Laser Interferometer Gravitational Wave Observatory. It's not one telescope, but two enormous L-shaped facilities, one in Washington State and the other in Louisiana. Each arm stretches 4 kilometers, long enough for lasers to bounce back and forth, measuring changes in distance smaller than a proton's diameter. The idea sounds absurd. Catch a whisper by building 2 giant rulers and waiting for space-time to twitch. For decades, nothing. The detectors hummed quietly, listening to the universe's stillness. Scientists tweaked mirrors, battled vibrations from passing trucks, even accounted for waves in the Gulf of Mexico. Then, in September 2015, the silence broke. A brief faint chirp, that's how it sounded when converted into audio, crossed both detectors within milliseconds of each other. The signal matched exactly what Einstein's equations predicted for 2 black holes merging 1.3 billion light-years away. In that instant, the universe spoke, and humanity heard it. Space had rippled, time had flexed, and relativity had finally sung its proof. You can almost hear it still. Whoop, a cosmic sigh too low for any ear. Here's your quirky fact of the night. The LIGO team delayed announcing their discovery for months. They were so careful that they suspected it might be a test, something secretly inserted into the data to check their vigilance. When they realized it wasn't a drill, the celebration was quiet at first. Then champagne happened, and probably a few tears. Since that first detection, the universe hasn't stopped humming. LIGO and its sister observatories, Virgo in Italy and Kaigura in Japan, have picked up dozens more signals, black holes colliding, neutron stars merging, space-time echoing like a struck drum. One event in 2017 even produced both gravitational waves and visible light, allowing astronomers to pinpoint the collision and watch the afterglow spread across galaxies. It was the birth of multi-messenger astronomy, seeing and hearing the cosmos at once. Historians still argue which moment was more revolutionary, Einstein's 1919 eclipse or LIGO's first chirp. Both proved space can bend, but gravitational waves showed it can move. Space isn't static, it's elastic, it can shiver, ripple, resonate. You imagine what those waves would look like if you could see them. Faint, concentric circles spreading outward from cosmic disasters, expanding endlessly, softening with distance but never truly dying. Each one carries information, how massive the objects were, how fast they spun, even a fingerprint of the final merged remnant. The universe has its own Morse code, and we've only just learned to listen. You chuckle quietly at the thought of Earth as a cosmic seismograph. While we worry about the day's little tremors, emails, traffic, the microwave beeping, space itself is conducting a slow-motion symphony around us. We're all vibrating just a little out of tune, and that's strangely comforting. A small, sleepy joke. Somewhere, two black holes collided billions of years ago, and the echo finally rocked a mirror in Louisiana just enough to make a physicist spit out their coffee. Beyond the humour lies something profound. Gravitational waves prove that even empty space isn't rigid. It's alive, flexible, capable of carrying messages across impossible distances. The next generation of detectors, like the planned space-based LISA mission, will measure these ripples from orbit, tracing the rhythm of the universe itself. And if you could somehow hear them directly, not as frequencies translated into sound, but as pure distortions of space-time, you might find the noise oddly soothing. Each wave passes through you silently, rearranging your molecules by a trillionth of a hair's breadth, then moving on. It's the universe breathing in and out. Historians still debate whether Einstein would have celebrated or simply nodded knowingly. After all, he once called gravitational waves a pure consequence of the field equations. But you suspect he would have smiled at the faint little chirp, humbled that the cosmos had finally whispered back. You let that whisper carry you now. The ripples fade, blending into the low, even pulse of your heartbeat. Somewhere, another pair of black holes begins their spiral, their gravity twisting space tighter and tighter until the next wave is born. And you, tiny witness, soft listener, float quietly in the aftermath, rocked by space-time's slowest lullaby. You keep drifting, still feeling that gentle hum, but now you start to wonder how anyone could know these bends, these ripples, these secret flexes of space-time are really there. You can't see curvature, can't scoop it up in a jar, so how do humans measure the unseeable? The thought feels absurd at first. Measuring space-time is like trying to weigh a sigh. And yet, somehow, astronomers have been doing exactly that for a century, weighing size, timing shadows, chasing milliseconds until geometry confesses. Your first stop is a long, quiet hallway full of ticking clocks, atomic clocks, laser clocks, satellite clocks, each one so precise it could run for millions of years before losing a second. Time, after all, is part of space-time, so measuring its flow means measuring curvature itself. A clock on a mountain runs slightly faster than one in a valley, because gravity curves time more strongly at lower altitudes. Einstein predicted this, and modern instruments confirm it daily. The difference is tiny, a few nanoseconds, but enough that GPS satellites must constantly correct their onboard clocks to stay honest. Without those relativistic tweaks, your phone would think your favourite coffee shop was 2 blocks away. So, yes, each time you ask for directions, your phone is quietly whispering to the cosmos, asking, "Hey, space, how bent are you right now?" The scene shifts. You're floating inside a gleaming white tunnel where 2 beams of light race down long vacuum tubes and bounce between mirrors. This is LIGO again, but zoomed into the finer details, the interferometer. Each beam serves as a ruler, comparing its travel time with the other. When a gravitational wave passes, one arm lengthens while the other shortens by an infinitesimal amount, and the interference pattern of the recombined beams shifts ever so slightly. That flicker is the fabric of reality stretching and relaxing. It's the most delicate dance floor ever built, and the dancers are photons. Historians still argue whether Michelson and Morley, the 19th century experimenters who invented interferometry, would have understood this future use of their device. They originally tried to detect the ether, that imaginary substance once thought to carry light waves. They found nothing, no ether, no preferred direction in space, and accidentally paved the road to relativity. The irony is delicious. By failing to measure the old universe, they handed the tools to measure the new one. You glide past other instruments now. Space telescopes track the wobble of starlight to infer unseen planets. Pulsar timing arrays listen for tiny shifts in radio pulses that betray the passing of gravitational waves. Even the cosmic microwave background, the faint afterglow of the Big Bang, has become a ruler of spacetime's ancient curvature. Satellites like Planck and WMAP have mapped it with eerie precision, showing that on the largest scales the universe is astonishingly flat, like a perfectly balanced trampoline stretched across infinity. But even flat here just means gently curved beyond our detection. Flat the way a lake seems flat until you sail far enough to vanish over its edge. A quirky bedtime fact. In 1971, physicist Joe Hafeel and astronomer Richard Keating carried 4 cesium atomic clocks aboard commercial jets, flying once eastward and once westward around the globe. When they compared their airborne clocks to ones left on the ground, the differences matched Einstein's predictions exactly. Time had literally stretched and compressed depending on altitude and direction. The experiment cost about $8,000, an absurdly small price to prove that spacetime is elastic. You may chuckle. Somewhere a government accountant once reimbursed a receipt labelled airfare relativity test. The universe offers subtler measuring sticks too. Quasars flicker irregularly, and their light arrives through a forest of lensing galaxies. By tracking those fluctuations, astronomers can chart the depth of cosmic wells. Neutron star collisions emit both light and gravitational waves, giving scientists a way to triangulate distances and calibrate the cosmic expansion rate. It's as if every corner of creation has agreed to serve as a ruler, a stopwatch, or both. Yet, even with all this precision, we still measure curvature indirectly. No one has ever seen spacetime itself. We infer its shape from how matter and light behave. Historians still debate whether that makes geometry a physical thing, or just the best story physics can tell. Maybe there is no fabric, just relationships, patterns, equations masquerading as cloth. But if it behaves like something that bends, ripples, and vibrates, perhaps that's real enough. Imagine yourself now as part of a vast laboratory. The atoms in your body mark points in the grid. The ticking of your pulse is a tiny clock. If space-time stretched even slightly, you'd feel nothing, but your atoms would know. Their bonds subtly renegotiated by the curvature around them. You are, in a sense, a living instrument measuring the universe's geometry simply by existing. A small, sleepy joke for the night. Technically, you're a walking interferometer, though instead of lasers and mirrors, you use coffee and mild confusion. The more we measure, the stranger it gets. Some regions of the universe appear to bend backward in time, others expand faster than light without violating relativity. Space itself seems to stretch, dragging galaxies apart while keeping local systems bound together. Measuring this expansion requires yet another ruler, the redshift of light. As the universe grows, wavelengths stretch, sliding from blue to red like a cosmic exhale. By mapping how much the light has reddened, astronomers reconstruct the scale of the universe across billions of years. And so the measuring never ends, from atomic clocks to telescopes spanning continents, from vibrating mirrors to whispering pulsars, humanity keeps taking space-time's pulse, one delicate beat at a time. You close your eyes and listen. If you could hear all those instruments together, the ticking clocks, the humming lasers, the steady whoosh of expanding space, it would sound like a faint, endless chord, a song of measurement, a lullaby of precision. Somewhere a beam of light just bounced off a mirror in a vacuum tube and told us, the universe moved by a trillionth of a hair, and you, lying there, moved with it. You open your eyes to something comfortingly familiar now, the slow curve of Earth beneath a morning sky. After all that cosmic bending, it's nice to come home to a planet you can actually stand on. But look closer. The curvature hasn't gone anywhere. It's just gone local, subtle and steady. You live on a ball of warped space-time, and even your coffee mug sits a few nanoseconds behind the clock on a mountaintop. Welcome back to the gentle end of the curve. You might have heard people say the Earth is round, but it's more poetic to say it's curved. That word carries both the geometry and the mood of it. Curvature is the universe's way of keeping things interesting, never quite flat, never quite straight. From the shape of the oceans to the flight paths of planes, that hidden roundness is always nudging you. Take a long-haul flight, say from Los Angeles to Tokyo. The line on the map bows over Alaska, looking inefficient, almost silly. But you're following a geodesic, the shortest path across a curved surface. The plane isn't turning north, it's obeying Earth's geometry, the same way planets obey spacetimes. The world bends, and so do you. You smile at the thought that navigators were using relativity long before Einstein formalized it. Sailors and explorers knew intuitively that the shortest route wasn't a straight one. The Polynesians read ocean swells, the Vikings followed arcs of sunlight, the first aviators used curved bearings to cross continents. They were all following the warp of the planet beneath their feet, or wings. Here's your historical anchor. In the early 3rd century BCE, a Greek scholar named Eratosthenes measured Earth's circumference using nothing more than shadows. He noticed that at noon in Syene, now Aswan, Egypt, the sun shone straight down a well, while at the same time in Alexandria, it cast a slight shadow. By comparing the angle and the distance between the cities, he calculated Earth's circumference with remarkable accuracy. Historians still argue how precise his distance figures were, but the idea was flawless. Geometry itself reveals curvature, a quirky modern tidbit. GPS satellites orbit about 20,000 kilometers above you, and their engineers must account not only for Earth's shape, but also for how gravity curves spacetime around it. The clocks on those satellites tick faster by about 45 microseconds per day, compared to clocks on the ground because they're farther from the planet's gravitational well. At the same time, their speed through space slows their ticking by 7 microseconds due to special relativity. The net correction, 38 microseconds, is constantly applied so your phone knows where you are. Without it, navigation errors would grow to kilometers within a day. Curvature keeps you punctual. If you look out over the sea, the horizon dips away, proof that your straight-line intuition is only local. Every sunrise and sunset is geometry in motion, the sun disappearing not because it sinks, but because you rotate away on a curved surface. Even weather follows these lines. Jet streams, hurricanes, and ocean currents twist with the Coriolis effect, a consequence of Earth's roundness and rotation. Historians still debate when humanity collectively accepted that the world is curved. Ancient sailors knew it long before medieval scholars did, and yet the myth of flat Earth ignorance persists, probably because it's too fun to let go. In truth, the curve has always been obvious to anyone watching a ship vanish hull first beyond the horizon. You stretch your thoughts farther, noticing curvature in everyday things. Raindrops bead into spheres because surface tension mimics gravity's tendency toward the most efficient shape. Soap bubbles form tiny universes with their own gentle warps of film. Even your eyeball is a lens carved by curvature, bending light into meaning. The cosmos repeats its favourite pattern endlessly, from galaxies to teacups. Here's a little joke to make you smile. If someone tells you they don't see the curvature of the Earth, remind them that's exactly the point. It's too big to fit in their field of view, but Earth's curve doesn't end at geography. Gravity keeps shaping time here too. Deep mines and tall towers mark different rates of seconds. In 2010, scientists at the National Institute of Standards and Technology built 2 atomic clocks separated by only 33 centimeters in height, and proved that the higher one ticked faster. You could, in theory, age imperceptibly quicker by sleeping on the top bunk. Congratulations, bunk bed immortals. If you were to leap upward fast enough to escape Earth's pull entirely, you'd find that every bit of your journey climbs out of slower time. The farther you move from mass, the less curvature, the faster your seconds. And if you could hover far above the planet, you'd see its space-time shape, an almost spherical dimple, shallow compared with the sun's but deep enough to hold the moon, the atmosphere, and you. Some physicists like to say Earth isn't falling around the sun, it's free-falling through curved space-time. That same description works locally. You're not standing on the ground, you're being ever so slightly deflected from your natural geodesic by the planet's surface pushing up at you. Every moment you're technically accelerating upward at 9.8 meters per second squared, held back from free fall. Gravity is the geometry's polite refusal to let you float away. You tilt your mind towards smaller scales now. The curvature here is gentle, but if you could magnify it, you'd see that every mass, even your own body, creates a tiny dimple in the surrounding spacetime. The effect is unimaginably small but real. Somewhere, your presence is making light bend by 1 part in a trillion. You're part of the global topography of gravity, a soft depression in the fabric of reality. Historians still argue whether thinking this way, imagining the Earth as a bowl of spacetime, helps or just confuses. Some educators prefer to say gravity shapes motion instead of space bends. But for you, lying here in the dark, both images merge: the curve beneath your feet, the arcs of stars above, the unseen dip of time around your heartbeat. A gentle fun fact before sleep tugs harder. Commercial jets fly roughly 10 kilometers high, where the horizon stretches about 400 kilometers away. At that height, you can actually see Earth's curvature if you know how to look, an almost imperceptible bow along the line of blue. It's subtle, but it's there, reminding you that the straight road home is always slightly round. You smile, feeling the curve cradle you. Earth's gravity holds your bed, your breath, your dreams in orbit, keeping you pressed softly into its dimple in space-time. Every falling raindrop, every orbiting moon, every spinning atom shares the same choreography. The universe bends at every scale, from the cosmic to the personal, and tonight, that bend feels like comfort, a slow, planetary hug. You stay cradled in that planetary hug for a moment longer, but something stirs in the space beyond. You can feel the gravity of the Milky Way wrapping itself around you, a deeper curve, invisible but undeniable. Yet when astronomers map the galaxy's mass, the numbers don't add up. The visible stars, planets and gas simply aren't enough to produce the curvature we see. Something unseen is flexing space-time. It has no light, no colour, no signature except the way it bends geometry itself. This is the hidden hand, dark matter. You drift outward, leaving the pale blue curve of Earth behind, into a region where billions of stars swarm together like glowing dust. The galaxy looks peaceful, but its rotation tells another story. In the 1970s, astronomer Vera Rubin and her collaborator Kent Ford studied the motion of stars in distant spiral galaxies. According to Newtonian and Einsteinian gravity, stars farther from the centre should move more slowly, like the outer planets of the solar system. Instead, Rubin found they were whipping around almost as fast as the inner stars. The outer arms weren't fading, they were holding tight, as if some invisible scaffolding were gripping them. Historians still argue whether her data alone proved the case, or merely revived an older mystery, but her quiet persistence changed astronomy. She showed that galaxies are not islands of light floating in emptiness. They are wrapped in halos of something unseen that provides the missing mass needed to hold them together. Without it, the galaxy would fly apart in a few rotations. You imagine that halo now, a vast sphere around the Milky Way stretching well beyond the visible disk, extending hundreds of thousands of light years. It has no glow, no particles you can catch, yet its gravitational influence is written across the motions of every star. If the galaxy were a snow globe, dark matter would be the invisible glass keeping all the glitter inside. A quirky tidbit for your sleepy mind. When Rubin first presented her results, some astronomers suggested the data might just be wrong. The instruments must have been misaligned, they said. Rubin calmly returned to the telescope, refined the optics, and gathered even stronger evidence. The universe, it turned out, had simply been hiding its weight. Now, more than 80% of the universe's matter is believed to be this unseen substance. It doesn't emit or absorb light, doesn't interact with electromagnetic forces, and doesn't seem to care about chemistry or heat. It only listens to gravity. And because it listens, it sculpts the shape of everything. You can almost feel it. A cold, silent web stretching across the cosmos, threads of invisible mass connecting galaxy clusters, like beads on a cosmic necklace. Computer simulations show that without dark matter, galaxies would never have formed at all. In the early universe, ordinary matter, hydrogen, helium, dust, was too smooth, too evenly spread. It needed the gravitational scaffolding of dark matter to clump and seed the first stars. Historians still debate what dark matter is. Some think it's made of undiscovered particles, WIMPs, weakly interacting massive particles, or axions perhaps. Others suspect it might be something even stranger, modifications to gravity itself, or entire populations of tiny black holes drifting unseen through galactic halos. Decades of detectors buried underground, floating in space, and chilling in liquid xenon have yet to capture even a single confirmed dark matter particle. The universe keeps its secret close. You drift through that invisible web, feeling how it bends light in its own quiet way. Gravitational lensing, the same cosmic mirage you saw earlier, reveals its fingerprints. When light from distant galaxies passes through clusters rich in dark matter, it warps into arcs and rings that can be measured. The amount of distortion tells astronomers how much mass is there, even when no light accompanies it. It's like reading the outline of a ghost by watching how curtains move as it passes. A small joke for the late hour. Somewhere out there, a dark matter particle is bumping into another and apologizing. Sorry, didn't see you. Closer to home, dark matter is everywhere too. It drifts through you right now, thousands of particles per second streaming through your body without leaving a trace. If you could somehow see them, you'd look like a constellation made of soft blue wind, momentarily intersected by invisible rivers of cosmic substance. It sounds eerie, but it's oddly peaceful, proof that you're immersed in something vast and unseen, sharing space with the scaffolding of galaxies. Even though it's invisible, dark matter shapes the curvature of space in a tangible way. The Milky Way's halo bends the paths of stars, planets, and even the sun's slow orbit around the galactic center. Without it, our solar system might never have stayed within this stable spiral arm. In a sense, every sunset you've ever watched is held in place by dark matter's invisible hand. Historians still argue whether Einstein would have approved of the idea. Some say he might have seen it as an extension of his own search for unifying forces. Others think he would have grumbled that inventing invisible stuff sounded too convenient. Yet the data keep speaking. Gravitational lensing, cosmic microwave background fluctuations, galactic rotation curves, all point to an unseen geometry beneath the visible one. There's something poetic about it, isn't there? The universe hides most of its mass not in brilliance but in silence. The stars are the fireworks. Dark matter is the quiet structure that lets the show exist. As you float through that invisible lattice, you begin to feel its rhythm. It doesn't move fast. It doesn't shimmer. It simply is. A calm, weightless pressure holding the cosmos together. You can think of it as the backbone of space, or maybe the lullaby bass note that underpins every visible melody. And though it never touches light, it bends it. Though it never glows, it defines every shining shape. The universe's grandest geometry depends on what it refuses to reveal. So tonight, as you lie there beneath your own thin slice of sky, remember, you're resting inside an invisible halo, a quiet ocean of unseen matter that holds the galaxy together. Even in darkness, gravity knows your name. You linger in that invisible ocean for a while, drifting between threads of unseen gravity, but soon you sense another movement, this one not pulling inward like dark matter's grip, but pushing outward, like the universe itself taking a long, slow breath. You're about to meet dark energy, the grandest and most mysterious bend of all, the one that doesn't curl space inward, but stretches it apart. Imagine you could zoom all the way out, beyond galaxies, beyond clusters, until the universe looks like a faint fog of light. If you measure the distance between those bright patches, you find something startling. They're moving away from each other faster and faster, not just coasting, not just drifting, accelerating. Space isn't content to sit still, it's expanding, and that expansion is speeding up. That revelation came quietly in 1998, when two teams of astronomers studying distant type, Ia supernovae, compared how bright those stellar explosions appeared with how far away they should be. The light was dimmer than expected, meaning the supernovae were farther than any steady expansion could explain. The only conclusion was that the universe's growth was accelerating, as if some invisible pressure were pushing everything outward. Historians still argue about who deserves the most credit for that discovery. Saul Perlmutter's Supernova Cosmology Project, or Brian Schmidt and Adam Rees's High Z team. But both reached the same shocking result within months of each other. Einstein, it turned out, had once introduced a cosmological constant to keep his equations from predicting an expanding universe, then later called it his greatest blunder. Yet the data suggested that constant might actually exist after all. The blunder had been in doubting it. You smile at the irony. The universe really does enjoy an encore. But what exactly is this outward push? We call it dark energy, though that name hides more confusion than clarity. It isn't energy in any familiar sense. It doesn't fuel stars or power engines. It's more like a property of space itself, a kind of built-in elasticity. As the universe expands, there's more space, so there's more of this energy, and so the expansion accelerates even more. It's the ultimate positive feedback loop. You picture it as a slow-motion stretch, the cosmic fabric elongating everywhere at once. Galaxies don't move through space, they're carried with it, like raisins baked into an ever-rising loaf of bread. From within the dough, every raisin sees every other one moving away. That's what we see when we gaze at distant galaxies. We're all raisins in the same rising universe. A quirky tidbit. In 2011, the Nobel Prize in Physics went to those supernova hunters for confirming dark energy's existence. During the ceremony, one of them joked that they were honoured for discovering something we still don't understand. The universe, he said, is about 70% dark energy, meaning we understand only 30% of it on a good day. It's humbling to realise that the very geometry of the cosmos is dominated by something we can't measure directly. If dark matter bends space inward into comforting curves, dark energy bends it outward, flattening and stretching it like taffy. Together they form the cosmic tug-of-war that defines everything. One pulling structure together, the other pulling emptiness wider. You drift through that expanding fabric now, feeling it widen beneath you. Galaxies slide apart like slow tectonic plates, but the motion is smooth, silent. Even the light between them stretches, its wavelengths lengthening into red, then infrared, then microwave. This stretching of light is the universe's pulse, the redshift, and it grows with time. Someday, distant galaxies will slip so far away that their light will never reach us. The night sky will empty, leaving only the faint local cluster of stars, our own small island in an ever-darkening sea. Historians still debate what dark energy actually means. Some describe it as a cosmological constant, a fixed energy density of the vacuum. Others think it could be a dynamic field, nicknamed quintessence, that changes over time. A few suggest our theories of gravity themselves might be incomplete, that maybe space bends differently on vast scales than Einstein's equations predict. No one knows which story will win. For now, we simply measure the expansion and watch it accelerate. Here's a tiny, drowsy joke. Physicists once thought the universe might end in a big crunch. Now they worry it'll die of cosmic middle-age spread. You can almost feel the acceleration if you let your imagination lean into it. Space isn't pushing galaxies like wind, it's expanding everywhere at once. Even between the atoms in your body the effect exists, though it's far too small for chemistry to notice. If you could freeze time and draw a grid over the universe, you'd see each cell of that grid slowly growing. The grid itself is doing the moving, everything inside just rides along. Astronomers use delicate tools to track this expansion. The baryon acoustic oscillation patterns imprinted in the large-scale structure of galaxies act as a kind of ruler, showing how much the universe has stretched over billions of years. The WMAP and Planck satellites measured tiny fluctuations in the cosmic microwave background that reveal the same story. Geometry dominated by something invisible and repulsive, not in the social sense, though the metaphor works. If the trend continues, in tens of billions of years, galaxies will drift so far apart that their light can no longer bridge the gap. Future astronomers, if any still exist, will see only their own galaxy and might conclude, wrongly, that the universe is static. In a way, we live at a privileged moment. The expansion is visible, measurable, and still friendly enough to let us notice. Yet even this relentless stretching carries a certain calm. Space bends and flexes, but it never breaks. The expansion doesn't tear apart galaxies or planets. Gravity holds local structures intact. You, your neighbourhood, the Milky Way, all safe within small gravitational wells while the cosmic tide rises around you. It's the gentlest apocalypse imaginable. Historians still argue whether to call dark energy a property of the vacuum or an entirely new substance. Some whisper about phantom energy, which could accelerate expansion so fast it eventually rips even atoms apart in a hypothetical big rip. Others bet on an eternal steady stretch. The truth hides somewhere between mathematics and poetry. You float, listening to the slow exhale of space. The curve you once felt tugging inward now feels like a long outward sigh. Galaxies recede like sparks on cooling embers, and the cosmic fabric hums, content to stretch forever. Maybe the universe isn't ending or beginning, it's breathing. One vast inhale of gravity, one slow exhale of expansion, and you, tiny observer, are caught perfectly in the middle of the breath. You hang suspended in that long cosmic exhale, the faint stretching of space tugging at your thoughts like a tide. But then, your mind turns to a harder question. What happens when geometry stops making sense? When the curves become too steep, the equations too tangled, and the fabric of space-time itself begins to fray? You're entering the frontier where gravity meets quantum physics, the place where geometry, the old reliable map of reality, starts to break down. It begins innocently enough. Einstein's general relativity describes gravity as curvature, smooth and continuous. Quantum mechanics, on the other hand, says the universe is granular, made of discrete bits of energy and probability. Both theories work beautifully, until you try to make them talk to each other. Then everything falls apart faster than an undercooked soufflé. You drift toward one of those impossible edges, the center of a black hole. Relativity predicts a singularity there, a point of infinite density where the curvature of space-time becomes undefined. But quantum physics doesn't like infinities. It wants uncertainty, not impossibility. Somewhere in that mathematical collision, our understanding evaporates. Historians still argue whether singularities are real places or just signs that our theories have hit their limits. Some say they're clues, breadcrumbs leading toward a deeper framework where gravity and quantum mechanics finally merge. Others think they're like warning labels, here be dragons. Whatever they are, they remind us that the map of space-time is incomplete. Let's linger here for a second. Picture the very early universe, just after the Big Bang. Everything, everywhere, packed into a volume smaller than an atom. Relativity can describe the expansion beautifully once it begins, but the instant before that, the equations dissolve into nonsense. The same infinities appear, the same contradictions. To truly understand the beginning, or the heart of a black hole, we need a theory of quantum gravity, and that, sleepy traveller, is physics' most elusive dream. A quirky bedtime fact: the search for this theory has been going on for nearly a century. Einstein himself spent his later years chasing it, scribbling equations in solitude while the world around him shifted toward quantum mechanics. He never found it, though he suspected it must exist. Historians still debate whether his insistence on a deterministic universe blinded him to the probabilistic beauty of the quantum world, or whether he was simply ahead of his time, reaching for a synthesis no one else could yet imagine. You drift now between the scales, vast gravity and tiny quantum foam. Imagine zooming in on space-time itself until distances shorter than a trillionth of a centimetre begin to wobble. The smooth fabric turns jittery, frothing with virtual particles that pop in and out of existence. This is the Planck scale, where even up and down stop behaving, and space becomes less like a fabric and more like a flickering sea of probability. Some physicists think this foamy chaos might be the true foundation of reality, with space-time emerging as an average behaviour of something deeper. It's like mist rising from water. You can see the fog, but not the droplets that create it. Maybe space isn't continuous at all, but a kind of statistical illusion. You may find the idea strangely calming. If space itself can dissolve and rebuild, then maybe every moment, every breath, every heartbeat is the universe reassembling you, frame by frame, out of fluctuating geometry. There are a few contenders vying to describe this mysterious level of reality. One is string theory, which replaces point-like particles with tiny vibrating loops of energy. Each vibration mode corresponds to a different particle, and the strings naturally generate gravity through their oscillations. The math is elegant, almost too elegant. Some say it's closer to art than science. But it demands extra dimensions, up to 11 of them, most curled too tightly to see. Another is loop quantum gravity, which imagines space as a network of discrete loops woven together like microscopic chainmail. In this picture, space-time is quantized, built from finite chunks of area and volume. Geometry becomes digital rather than analog, a cosmic pixel grid. Both theories try to remove singularities, smoothing out the infinities that haunt relativity. Some versions suggest that inside a black hole, space-time doesn't collapse forever, but rebounds, a bounce instead of an end. Others hint that the Big Bang itself might have been a rebound from a previous universe's collapse. The cosmos could be eternal, cycling endlessly through expansions and contractions. Historians still argue whether these ideas are science or philosophy, since testing them directly seems impossible. But indirect clues keep emerging. Tiny patterns in the cosmic microwave background might carry whispers of quantum geometry. Gravitational waves could someday reveal whether space-time truly ripples, or if it flickers in discrete jumps. Even black hole radiation, the faint glow predicted by Stephen Hawking, may hold the key, encoding quantum information in the most extreme gravitational setting imaginable. A sleepy joke floats by. Maybe the universe is just trying to remind us not to take flat surfaces too seriously. You let the thought settle. Geometry breaking down isn't a failure, it's an invitation. The fact that our equations reach limits means there's more to learn, more mystery humming beneath the surface. The curves you followed from Newton to Einstein to the present aren't wrong. They're just approximations of something even subtler. Imagine the universe as an enormous quilt. Relativity describes the stitching, the smooth, curved patterns that hold everything together. Quantum theory describes the threads themselves, vibrating and unpredictable. But there must be a weaver somewhere in the math, a deeper rule that connects both pictures. Maybe it's simplicity itself, maybe chaos, maybe something we can't yet imagine. Historians still debate how close we are. Some say quantum gravity could emerge within decades. Others think it's a puzzle meant to stay unsolved, a cosmic Zen koan. But in your drifting mind, the paradox feels less like a problem and more like poetry. Space bends, time flows, equations break, but meaning doesn't. You inhale softly, feeling the edges blur, the boundary between the known and the unknown, between geometry and dream. Even when the math fails, the universe continues to hum. And maybe that's the point. The cosmos doesn't care whether we understand its bends. It keeps curving, keeps expanding, keeps singing its equations into being. Somewhere, beyond the reach of theory, space-time ripples in quantum laughter, folding and unfolding itself like origami made of light. And you, small observer, are folded gently within it, safe in the frayed corner where geometry gives way to wonder. You linger at that frayed edge of geometry for a while, watching the shimmering line where Einstein's smooth space-time meets the pixelated sea of quantum possibility. It's the most uncertain frontier in science, and maybe the most beautiful. But as your thoughts drift onward, you notice something else glinting in that chaos. Theories, wild and hopeful, shimmering like soap bubbles over the dark foam. These are the alternate visions of the universe, born from physicists' late-night coffee, chalk dust and dreams, the wild attempts to fix the bends. You begin with string theory, the celebrity of the bunch. It began quietly in the late 1960s as an odd mathematical model for subatomic particles, but soon inflated into something much grander. In this story, every fundamental particle is not a point but a tiny vibrating string. The differences between electrons, quarks and photons aren't different things at all. They're different musical notes played by the same instrument. Gravity, electromagnetism, nuclear forces all arise from the harmonies of these strings. You picture the universe as an enormous harp of energy, each string no longer than 10 to the minus 35 meters, plucked by quantum uncertainty. Matter is music, and space is the instrument it resonates through. The poetic appeal is undeniable. Even Einstein might have approved of the unity, though he'd probably roll his eyes at the 12-dimensional math. Historians still argue whether string theory is discovery or daydream. Some call it the theory of everything, others the theory of nothing. It has produced elegant mathematics but precious little testable evidence. To hide its tiny strings and extra dimensions, the theory must wrap those dimensions into shapes called Calabi-Yau manifolds, geometric origami so intricate they make your head spin. According to some versions, there could be more than one universe, billions, each with its own shape, constants and physics. Together they form the multiverse, a concept both intoxicating and infuriating. A quirky fact before you drift too far. The string landscape, as physicists call it, may have around 10 to the 500 possible solutions. That's a 5 followed by 500 zeros, a number so absurdly large it makes counting grains of sand on all the beaches of Earth look like kindergarten arithmetic. Somewhere in that impossible library, perhaps, is the universe you know, the one with just the right mix of constants to make stars and cats and coffee. You glide through those folded dimensions now, slipping between possibilities like pages in a dream. One universe hums a little faster, another slower. In one, gravity is stronger. In another, atoms can't exist. It's dizzying but strangely soothing, proof that our particular corner of reality is both rare and inevitable. Historians still debate whether this multiverse idea is science at all. You can't easily measure what lies beyond your own space-time after all. But some cosmologists argue that the theory might leave fingerprints, subtle imprints in the cosmic microwave background, where other universes might have brushed against ours long ago. No evidence yet, but the search continues, because curiosity is humanity's favourite habit. If string theory feels like a symphony, then loop quantum gravity is more like jazz, improvised, granular, raw. It began as a rebellion against string theory's need for extra dimensions. Instead of imagining new spaces, loop theorists decided to quantize the existing one. They describe space-time as a network of discrete loops, tiny spin networks woven together like a cosmic chainmail. In their view, space itself comes in quanta, finite chunks of area and volume. You can't divide a distance forever, eventually you hit geometry's smallest note. You imagine yourself zooming in on that texture until smooth curves dissolve into tiny interlocking rings. It's like standing too close to a painting and seeing only brushstrokes. Gravity, in this picture, emerges from how those loops twist and knot around one another. The result is still untested, but it erases the infinities that plague black holes in the Big Bang. At the centre of the hole, there's no singularity, just a region where space-time rebounds, creating what some theorists call a Planck star. A small, sleepy joke. Physicists may never agree whether the universe is made of strings or loops, but they all seem tangled up about it. Beyond these two main contenders, other ideas swirl in the dark. There's causal set theory, where space-time is a growing web of discrete events, like dots connected by arrows of cause and effect. There's emergent gravity, proposed by Eric Verlinde, suggesting gravity isn't fundamental at all. It's a byproduct of entropy, a kind of thermodynamic illusion. There's asymptotic safety, holographic duality, and the deliciously mysterious ADS/CFT correspondence, which claims that everything in a volume of space can be fully described by information written on its boundary, a universe as hologram projected from a cosmic screen. Historians still argue whether these models contradict one another or simply describe different faces of the same truth. Maybe space-time is both continuous and discrete, both inside and out, both string and loop, note and network. You drift through that intellectual cosmos, half dreaming, half learning. Equations swirl past like constellations, symbols glowing faintly, their meanings half remembered. There's something comforting about seeing so many minds reaching toward the same mystery, each tugging a thread from the tangled fabric. Maybe the universe is too vast for any single theory. Maybe it takes a tapestry of ideas to capture its shape. One more quirky bedtime tidbit. In 2017, scientists discovered that black hole thermodynamics, the rules that describe how they radiate and lose mass, can be interpreted as the laws of space-time geometry itself. It's as if the surface of a black hole is a literal book of physics, its equations etched into its horizon. Some physicists think the entire universe works that way, the information content of every region written onto its boundary, like data encoded on the skin of reality. If that's true, then maybe you are already a pattern, an arrangement of information woven into space-time's outermost layer, a cosmic hologram of consciousness, dreaming of curvature. Historians still debate whether that's philosophy or physics, but you decide not to care. The line between science and poetry feels thin here, and the universe probably doesn't mind being both. You smile faintly. Maybe all these theories, strings, loops, holograms, are just different metaphors for the same truth. That space bends because information itself bends. That geometry is not a static thing but a story constantly rewritten. The equations whisper as you drift past them. They don't compete. They harmonize like chords resolving in a slow, infinite cadence. Somewhere among those harmonies, reality hums quietly, and you float inside the note. You linger among those whispering equations until they dissolve into a gentle darkness. The universe quiets again, and in that hush, another question begins to rise. Not about matter or energy this time, but about you. How does a mind built for flat floors and round doorknobs grasp a cosmos made of curved space-time? You've followed the bends all the way from Newton's tidy stage to Einstein's flowing fabric, but now it's time to ask why it all feels flat when it isn't. Welcome to the fault line between human perception and cosmic truth. You open your inner eyes and look around your familiar world. Everything seems stable, Euclidean. You reach for your glass of water, confident that straight lines stay straight, that right angles add up to 90 degrees, that the floor beneath you doesn't tilt into the curvature of space-time, and you're not wrong, at least not locally. Your brain, evolved for survival, does something astonishingly clever. It flattens the world. Each of your senses is a translator. Eyes turn photons into edges, ears turn pressure waves into order, skin converts gravity into the reassuring sensation of down. Your neurons take the grand, bent geometry of reality and redraw it as a practical, bite-sized version that fits inside a skull. You might say your mind is the ultimate cartographer, always simplifying the cosmic terrain into a tidy 2D map marked, "Here be furniture." A bit of history for your pillow. Even in the early 19th century, some mathematicians suspected space might not be perfectly flat. Nikolai Lobachevsky and Janos Bolyai worked out entire systems of non-Euclidean geometry, where triangles had strange sums and parallels behaved like moody teenagers. But when they showed their ideas to philosophers, most dismissed them as mathematical curiosities. The world felt flat, and humans trust feelings far more than math. It wasn't until Einstein's relativity arrived that anyone realized those strange geometries described the universe itself. A quirky modern tidbit. Psychologists once ran experiments where people were asked to draw straight lines while standing on a rotating platform. The lines curved without them realizing it. Their brains silently corrected for the motion, believing they were still. It's the same trick your inner ear performs every time an airplane banks. Perception edits curvature out of your experience. Otherwise, you'd feel seasick just standing on Earth's spinning sphere. You drift deeper into that idea, and suddenly you're standing, metaphorically, inside your own skull, watching neurons flash. They're working in 3 dimensions, but their wiring encodes something closer to 2.5. Your visual cortex assumes light travels straight. Your sense of distance assumes parallel lines never meet. These assumptions are evolutionary hacks. On the savannah, no one needed to solve Riemann tensors. You just had to throw a spear accurately enough to eat. Historians still argue whether the human mind can ever truly imagine curved space-time. Artists and mathematicians try, but even they rely on metaphors. Rubber sheets, funnels, grids, flat stand-ins for a 4-dimensional reality. Maybe consciousness itself is Euclidean by default, forever painting over the curves with comforting straightness. You can test the illusion easily. Look up at the night sky. The stars form crisp constellations as if pinned to a dome. But each of those points lies at a wildly different depth, scattered across thousands of light years. Your brain compresses the distances into one surface, a cognitive shortcut that lets you admire Orion without vertigo. The truth, curved and stretched and shifting with time, is hidden behind perception's polite lie. Another little bedtime fact. Astronauts returning from orbit often report a sense of overview effect, a deep emotional shock when they see Earth's curve against the black. It's not just beauty, it's cognitive dissonance. For the first time, the mind witnesses curvature directly, and something rewires. The horizon becomes proof that geometry isn't abstract. It's alive, it's home-shaped. You chuckle softly. Maybe that's why humans keep building domes, from ancient temples to modern observatories. Somewhere deep down, we recognize that the heavens curve, and we mimic that shape when we reach toward them. Still, your flat world instincts cling tight. Architects design straight corridors, map makers flatten continents, digital screens enforce right angles. Only when you travel long distances, across oceans, through space, or deep into thought, does curvature assert itself again. The airplane's great circle route, the GPS's relativistic corrections, the slow precession of your own orbit around the sun, all gentle reminders that flatness is just convenience. Historians still debate whether early humans who watched ships disappear over the horizon understood curvature as concept or simply as mystery. But perhaps they didn't need words. Maybe they felt it in their bones, the same faint pull you feel when you watch the moon rise and sense without thinking that space itself must be round. A sleepy joke to lighten the mood. Philosophers have argued for centuries about whether reality is curved or flat, but your cat has always known. It curls itself into the shape of space-time every time it naps. The more you think about it, the more tender the illusion seems. The brain hides curvature not to deceive, but to comfort. It filters the vastness into something walkable, breathable, survivable. If you truly perceived the world's bends, you'd never dare move at all. Every step would feel like rolling downhill on a planet you can't see the edges of. And yet, there's a quiet joy in realizing the truth. Once you know the stage is curved, every sunrise, every falling leaf, every orbiting satellite becomes part of a shared geometry that ties you to the cosmos. You're not apart from the curvature. You are curvature, a local wrinkle in space-time aware of itself. You take a slow breath, feeling that thoughts settle. The world around you doesn't look any different. Your walls are still straight, your ceiling still flat. But you know now that underneath, everything is flexing ever so slightly. The room itself is a tiny pocket of curved space, your own personal coordinate system drifting through the galaxy's deeper bend. Maybe perception will never catch up with cosmic truth. Maybe it doesn't need to. The universe bends, the mind straightens. Between the two, meaning emerges, a compromise, a handshake across dimensions. As your eyelids grow heavy, the stars above you blur, flatten, then fade. But you can almost sense their true positions, curving through space-time, each beam of light a messenger bent gently by gravity, heading straight into your dreaming mind. You drift in that half-dream where you can feel both the steady weight of your body and the slow swing of the planet beneath it. The thought settles softly. You're not merely an observer of curvature. You live inside it. Every cell in you, every rhythm of breath, every heartbeat, every blink is an act of participation in space-time's constant flex. You're part of the bend. Start simple. You lie still, but the Earth beneath you is spinning about 1,600 kilometers per hour at the equator, orbiting the Sun at 30 kilometers per second, while the Sun orbits the Milky Way at 230 kilometers per second. That motion isn't against the curve, it is the curve, every trajectory drawn by the geometry around it. If the bending stopped, the paths would vanish, and so would the sense of direction itself. You, me, everyone. We're commuters on space-time's subway, carried along invisible tracks carved by gravity. You might picture yourself floating above Earth again, watching continents slip past. You're falling forever, tracing a perfect geodesic that happens to close in on itself once every 365 days. It feels stable because you and the planet are sharing the same curvature. Everything near you is dropping through space-time together. The air you breathe is falling, your coffee cup is falling, the moon is falling. The only reason the cup doesn't drift away is that the table keeps pushing up on it, refusing to follow the curve completely. That gentle pressure is what your nerves interpret as weight. Here's your historical fact. In 1665, while an epidemic kept him home from Cambridge, Newton realized that the same force that pulls an apple downward keeps the moon in orbit. Centuries later, Einstein refined the picture. Gravity isn't a pull at all, but the shape of the journey. Still, both stories describe the same truth. You're never standing still. You're continuously responding to curvature. A quirky tidbit. The human inner ear, the vestibular system, detects acceleration but not constant motion. Because orbital motion is steady, astronauts in free fall feel nothing. They call it weightlessness, but it's really perfect obedience to geometry. Every time they drift through a spacecraft, they're moving along spacetime's truest line, unopposed. Think of your own body as a tiny gravitational system. Every atom in you contributes to spacetime's shape, however minutely. Your mass warps the grid just enough that photons passing through you are delayed by about 1 part in a trillion. It's an imperceptible dent, but it exists. In a universe made entirely of curves, even a thought has physical presence. It takes time, and time curves. Historians still argue whether Einstein's field equations imply that consciousness itself could affect spacetime, or whether that's poetic overreach. But physicists agree on this. Energy and mass are interchangeable, and thought consumes energy. Each flicker of neuron, Each electrical whisper in your cortex sends out a faint gravitational echo. The cosmos listens, even if only by a fraction of a whisper. You chuckle softly. You're literally making gravity while trying to fall asleep, a multitasking marvel. Zoom out again. Cities glow like neurons on the dark hemisphere. Planes trace luminous arcs. Tides rise and fall in response to the moon's curved invitation. Life itself organizes around geometry. Trees reach upward along the gradient of gravitational potential. Rivers carve valleys that follow the slope of space-time. Blood moves in pulses that depend on pressure differences shaped by Earth's pull. The very definition of up is local curvature. You might wonder if there's anywhere in the universe where space doesn't bend. The answer, technically, is no. Even the emptiest void still hums with virtual particles, tiny fluctuations giving the vacuum a faint mass-energy density. That means space-time is never perfectly flat. It's always slightly arched by whatever energy it contains. The cosmos cannot help but curve. Bending is its resting state. A playful moment before the next drift. Imagine trying to build a truly flat room. You'd have to remove the influence of every planet, star, and photon. Even then, quantum fluctuations would wrinkle it. The straightest wall in existence still bows, just so slightly, toward the nearest concentration of mass. Architecture, it turns out, is done on borrowed geometry. Historians still debate whether living inside curvature changes how we should think of ourselves. Are we passengers or co-authors? Some philosophers argue that by rearranging mass, building cities, dams, satellites, we're reshaping the local gravitational field and thus altering spacetime's geometry, however modestly. Every bridge, every orbiting probe is a human fingerprint pressed into the cosmic fabric. Look up. Well, metaphorically, since you're already horizontal. The International Space Station circles Earth every 90 minutes. Its path is pure geometry, continuous free fall combined with forward motion. Inside, pens float, astronauts glide, and clocks tick slightly faster than those on the ground. Their lives literally unfold along a different curve of time. When they radio home, they're speaking across diverging timelines, so tiny a difference you'd never notice, but real. You can sense a quiet symmetry here, the macro and the micro, the cosmic and the personal. Galaxies swirl because of spacetime's architecture. So do hurricanes, coffee in a mug, and dreams spiraling into sleep. Everything you experience is some form of motion through curved time. You don't just occupy space, you flow through it, leaving a wake of tiny gravitational ripples. A sleepy joke: if you ever feel bent out of shape, remember, that's technically accurate cosmology. The realization is strangely tender. To live inside curvature means to belong utterly. You're woven into the same continuum that binds galaxies and photons. When you move, space-time adjusts. When you rest, it settles with you. You're not on the fabric of the universe, you are part of its weave, a mobile knot of mass energy giving form to the very geometry that carries you. Historians still argue whether that's a comforting thought or an existential one. But lying here, half dreaming, it feels peaceful. The bending isn't confinement, it's embrace. The curve doesn't trap you, it carries you. So you let yourself sink a little deeper into the mattress, feeling Earth's slow pull, feeling the planet's own orbit tug gently on your atoms. Each breath adjusts the balance ever so slightly. Each heartbeat adds a micropulse to the gravitational field. You're participating effortlessly in the shaping of reality. Space bends, time sways, and you sway with it, part of the endless conversation between matter and geometry. Inside the curve, everything belongs. You drift somewhere between thought and dream now, carried along by the same gentle geometry that holds galaxies together. The curves around you widen until they're no longer local or planetary, or even galactic. They're cosmic. You're hovering at the edge of everything, where the universe itself seems to inhale and exhale, the slow breathing of existence. The bends you followed from apple trees to black holes now form one grand arc, the universe exhaling. Imagine it. Space itself expanding like lungs after a long-held breath. Galaxies are the dust motes caught in that motion, carried outward by the fabric beneath them. The further apart they are, the faster they recede, not because they're flying through space, but because space itself is stretching between them. It's a quiet, inexorable movement. There's no sound, no wind, no center. Everywhere is center. Astronomers once thought this expansion might slow over time, maybe even reverse into a cosmic collapse. Instead, it's accelerating. The cause, that mysterious dark energy, continues to urge the universe outward. Historians still argue whether this means the cosmos will expand forever, fade into cold darkness, or reach some graceful balance. Whatever the fate, what you're witnessing is geometry in motion on the grandest possible scale. You float past clusters of galaxies, superstructures so vast they defy comprehension. Each cluster is its own community of space-time dimples, tied together by dark matter, yet even those bonds stretch thinner as the universe exhales. Filaments of the cosmic web elongate, and between them yawns more and more nothingness. You might think of that nothingness as emptiness, but it's really the purest form of geometry, space unburdened by mass, unrolled into smoothness. A historical moment for your twilight mind. In 1929, Edwin Hubble measured that galaxies were receding, their light redshifted, proving the universe was expanding. He expected resistance. Instead, most scientists were delighted, except Einstein, who grimaced, realizing he could have predicted it if he hadn't added that cosmological constant years earlier. My biggest blunder, he called it, though later the constant came back as the symbol of dark energy. Historians still debate whether it was a blunder or foresight disguised as error. You smile sleepily. Even geniuses bend with the times. The further out you float, the slower time seems to move. From this vantage, the universe's expansion looks less like a rush, and more like a slow tide. Billions of years between ripples. Galaxies collide occasionally, merging like drifting soap bubbles, but overall the motion is serene. The Milky Way itself is on course to meet Andromeda in about 4 billion years. Their encounter will stretch space-time in exquisite new ways, birthing a larger, rounder galaxy, Milkomeda, a name both ridiculous and inevitable. Here's a quirky tidbit. Simulations of that future collision show that while billions of stars will move, very few will actually hit each other. Space, even inside galaxies, is mostly emptiness. The curvature spreads them apart faster than they can collide. When galaxies crash, it's geometry that rearranges, not destruction, but transformation. You can sense the rhythm now, the universe as an immense pulse of expansion and cooling. Early on, everything was dense and hot, curvature so sharp it nearly folded back on itself. Now it stretches smoother, the bends relaxing. The universe, in a sense, is aging into comfort. You might think of it as exhaling into middle age, no longer rushing to form stars, just letting the light fade gently into the background. Historians still argue whether time itself will ever stop if expansion continues forever. Some cosmologists predict a heat death, when the universe becomes uniform, every gradient erased, every star extinguished. Others imagine quantum fluctuations still bubbling in the darkness, occasionally spawning new bursts of space-time, offspring universes rising like sparks from cooling coals. But those distant futures are abstractions. What you feel now is the quiet balance between stretching and belonging. The same expansion that carries galaxies apart also carries your atoms with perfect precision. Even as the distances grow, the laws remain constant. The curvature never loses its grace. A sleepy joke for this cosmic scale. If you ever feel you're drifting apart from someone, remind yourself it's just universal expansion. It's not you, it's lambda. You let the humour fade into awe. The realization is immense. Space isn't empty, it's alive with change. Every second, more of it comes into being. The universe is still making room for galaxies, for starlight, for you. Each expansion adds more fabric to the grand quilt, a continuous creation woven from nothing but possibility. If you could hear the universe's breathing, it might sound like the low hum of cosmic microwave background radiation, the faint echo of its fiery youth, stretched by billions of years of expansion into a cool whisper. Astronomers have mapped that whisper, turning it into a portrait of the universe's early wrinkles. Those tiny fluctuations, those first uneven patches of density, are what eventually became galaxies, stars, and perhaps even this moment of thought inside you. Historians still debate whether the universe's shape, its overall curvature, is flat, open, or closed. Current measurements suggest it's almost perfectly flat, but almost carries a lifetime of meaning. The difference could determine whether the universe will expand forever, slow to a stop, or one day collapse back inward. Either way, geometry will write the ending. You're aware now of how the story loops. Space bends inward around mass, but on the larger scale it bends outward, creating both gravity's pull and expansion's push. The universe is a self-balancing act between contraction and release, like the steady rhythm of your breathing. Perhaps it's not a coincidence that when you relax, when you inhale slowly, exhale gently, you mirror the cosmos. The stars around you shimmer faintly as the exhale continues. You can almost see the future. Galaxies drifting apart until only a few remain visible, their light stretched into infrared ghosts. The fabric cools, the hum lowers, and space smooths out its last wrinkles. But before that quiet finale, there will still be countless cycles of formation and wonder, new stars born from the dust of old ones, new minds looking up and asking the same question you began with: why does space bend? And maybe, by then, the universe will answer not with equations but with calm, by simply existing in its perfectly curved repose. You take one last slow breath with it, matching your rhythm to the cosmos's, the inhale of matter, the exhale of space, the gentle balance between gravity and freedom. Everything bends, everything moves, everything rests in that eternal curve. You exhale too, softly as the darkness folds around you, no longer empty but full of quiet.